Yeah. Good evening, everyone. Am I audible? Hello.
Yes, sir. Yes, sir.
Yeah. Okay. Fine. Okay. So today we will basically recall week five. Already there was one live session on week five. So before starting, how was your quiz one? I mean, are you happy with the question? I mean, was the question easy or difficult?
Easy, sir.
Easy. Okay.
Yes, sir.
Sir,
Yeah.
good evening, sir.
Yeah. Good evening.
Sir, your voice is somewhat low.
Yeah. Is it? Now is it okay?
Yes, sir. It's okay.
Okay. Right. Uh, okay. So before starting, I mean, what I have planned to do in week five, do you have any doubt till week five? I mean, already we have one live session, so we can start with your question then.
Uh, Sir, I want to ask some questions from activity questions 5.5.
No, before going to the activity question, you have any conceptual doubt in week five?
Excuse
No,
me,
sir.
sir. Good
Then,
evening.
yeah, good enough.
Sir, I have one doubt. I've understood basically. I completed week 5 only today. So, yesterday I did
Okay,
not attend because I could not understand. So, I understood making a matrix and then a row echelon form and then, but the last part where we have to arrange the columns corresponding to the variables and make that set like t1 comma t2 minus t1, that part I am
okay,
getting confused. How to arrange that?
hmm. Hmm. Okay,
So
okay.
that one
Any
can you
other
help to
doubt?
recall?
Yeah, I will discuss this.
Sure, sir. Thank you, sir.
Any other doubt? So can some of, I mean, at least one of you can tell me what is basically nullity of a matrix? Because week five starts with nullity of a matrix, right? So can anyone
Sir,
tell me
nullity is
what?
the
Yeah.
number of independent variables in when the solution set is reduced to echelon form. Number of independent variables. That is the nullity.
Variables of what? I mean, you are given a matrix. So what are independent variables there?
Independent variable means that we can assign any value to that variable.
I mean, where are these variables coming from? So you are given just a matrix, right? Then what are those variables which you are talking about? How they are coming?
Sir, if we have a 3 by 4 matrix,
Okay.
then the number of rows are 3 and columns are 4. That 4
Mm-hmm.
represents the number of unknowns.
Ah, okay. But how? I mean, why? I mean, why we need number of unknowns? I mean, what are we calculating basically?
We are calculating the null space. So
We are
what all
calculating a
values
null
of
space. Correct.
uh,
What is null space?
so null space are those set of values which makes the right hand side of the equation 0.
The solution set is the null set.
Solution
Null
set
space.
of. Right. So, and what is nullity?
The
Nullity
number
is
of
Number
independent
of independent variables.
dimension.
number of independent variables in all the equations
Okay.
taken together.
I mean,
One
exactly
After
we can
RRE,
calculate it. Yeah, that's okay. Uh, and what is rank? Rank we have studied in week four, right?
Sir,
yes.
if
Number
you
of dependent variables.
no,
No.
no,
What
no,
is
no.
rank?
Rank is what, sir. If we write the equations in homogeneous form, then rank is the number of non-zero rows which we
Okay.
get after reducing it to row echelon form.
Okay. Okay.
So it is irrespective of homogeneous and non-homogeneous, right?
The
Rank.
number of
I
dependent
mean, we are
variables.
interested in homogeneous because there is a reason. I mean,
So
if
number
you
of
see,
dependent variables. That is the rank.
okay, okay, fine. So yeah. So let me start from here. First of all, what is null space? Make that very clear. What is null space of a matrix? Okay. Suppose I have a matrix A. A is an M cross N matrix. Okay. So there are m rows and n columns, right? Correct? So
Yes.
suppose I have, for example, I have 2 cross 3. A 1 1 1 2 1 3 2 1 2 2 2 3. So this is a 2 cross 3 matrix, correct? So the variables which you are talking about will be like this: x1, x2, x3, right? 3 variable will be needed. So basically, when I am talking about a m cross n matrix, this null space is basically a subspace of Rm. You know what subspace is, right?
Hmm.
So it is a subspace of Rm, and how this subspace is defined? So this x is coming from Rm such that Ax equal to 0. Okay, so this is the definition of null space. Okay, so this tuple, this x1, x2, x3, all these are coming from R3 for a 2 cross 3 matrix, right? Is it clear? Sorry, this should be Rn. I mean, 3, this is N. Okay, so this is coming from R3, and all those x1, x3, x1, x2, x3 we need, for which this equation will be satisfied, Ax equal to 0. Is this part clear? That is the definition of null space, right?
You mean the solutions?
Basically solution set of Ax equal to 0, where A will, I mean the matrix which we have started with, that will work as the coefficient matrix.
Okay.
Okay. But actually the definition of null space is basically, it is a subspace of Rn for a m cross n matrix such that Ax equal to 0. I mean, when I multiply A with that vector, that will give me 0 vector. Okay. Now I am claiming it is a subspace, but we know that we have to check whether it is a subspace or not, right? So I have mentioned 3 points in previous week, I mean before the
Yes, sir.
quiz.
Yes, sir. Existence of
So
0.
so is 0 exist here? I mean, does 0 exist here?
If
Yes,
it
sir.
is a homogeneous solution, homogeneous system, then
0
of
must
course
be a
0
solution,
0
right?
is always the solution.
Always exists because A into 0 is 0, right? So 0 exists here. So let me call it n of A. So 0 is inside n of A, correct?
Second
Now
condition
what
is
was the second one?
closure on addition.
Closure or addition. So if x1 and x2 both are in A, does x1 plus x2 belongs to NA?
Yes, sir. We can prove it.
It is,
We
because
have already proved in one of the activity questions.
exactly. So this is basically, we have to show this is 0. So this I can write as x1 plus x2, and as x1 is in NA, so it is 0. Again, x2 is in NA, so it is also 0. So 0 plus 0, that is 0. Correct?
Excuse me, sir.
So x1 plus x2 belongs to NA.
Sir, this is
And
same as saying that if x1 and x2 is solution, then x1 plus x2 is also solution.
Exactly.
Closure
Correct.
on multiplications.
Closure on scalar multiplication. So
Yeah,
if
scalar
C is a real number, x is in NA, then A of Cx, that is same as C of Ax. Now Ax is 0, so C of 0 is 0. Okay, so Cx is in NA. So this NA, this null space, that is a subspace. That part is clear, right?
Yes, sir.
So when we are talking about subspace, it must have a basis, correct? Because subspace itself is a vector space, so it must have a basis, right?
Yes.
So we can talk about the dimension of this subspace, correct? Is this clear?
Yes.
So it is a
Yes, sir.
subspace.
Yes, sir.
So we can talk about the basis of it, and so we can calculate the coordinate
If
of
it
the
has
basis.
basis, then it's
So
yes.
yeah, so it must have some dimension, and that dimension is basically the nullity of a matrix. Okay, so that is the definition of nullity, dimension of null space of A. Okay, this is the nullity of a matrix. Okay,
Got it.
so when we are talking about nullity of a matrix, we basically are thinking of some vector space on Rn. Suppose the matrix is m cross n, that depends on the value of n. So subspace of that Rn such that it satisfies this one, Ax equal to 0. And as it is a subspace, we have already checked it is a subspace. The dimension of the subspace is basically nullity of the matrix. Okay. Now, as you can already see, according to this definition, this is nothing but the solution space of Ax equal to 0, where A is basically working as the coefficient matrix for the system of linear equation. Clear? Till this part it is okay?
Sir, would it be always equal to n?
Huh?
Because a subspace of Rn. Okay.
Subspace are Rn, so it may not be n. It
Yes, sir.
can be n or it can be less than n.
Less than n, right?
Okay, it cannot be greater than n. That's for sure. Okay.
So that's why
Okay,
it is
so
satisfying all the three axioms over here, sir.
Can
Sir,
you repeat your question?
That's why it has to satisfy all the three axioms over here.
Exactly. Because it is a subspace, so it will satisfy all the axioms of subspace.
Okay, thank you.
Okay. Yeah. So till this point it is okay. So let me take an example here. So let's start with a easy example. 0, 1, say -1. So I have taken already in row digitization form. So this is your matrix. Okay. Now I am asking you to calculate, first of all, what is your null space and what is your nullity. These two I am asking you to find out.
Nullity is 1.
Nullity.
Nullity is 1. So before calculating nullity, let's calculate null space first. Okay. So what will be its null space? How we will calculate it?
1 minus
x1,
1.
x2, x3.
So basically, it is all this x1.
We will
x2,
write some
x3
dependence
will
in
be-
terms of independence.
Correct. So basically, it has to satisfy this equation, right? All those x1, x2, x3. So basically, we have to find the solution of this equation, system of linear equation. Correct? Ax equal to 0. So what is this? This is
-1 and x1 equals to 1.
X1 is
x1 equals to 1 and x2 is -1.
not 1. x1
X1
plus
plus
x3 equal to
x3
0
equal to 0.
and x2 minus x3 equal to 0. Correct?
Yes, sir.
So it is already in row reduced echelon form. So if you want to see it in terms of dependent and independent variable, which we have already learned. So this is a pivot element. This is a pivot element. There is no pivot element in the third column, right? Because there is no third row. So this third variable
the
that is
0 matrix should be 2 by 1 now, sir. 2 by 1 matrix. How it is 3 by 1?
no, why 2 by 1? This is 2 cross 3, right? 2 row and 3 columns. So it should be 3
The
cross
0
1.
0 matrix I said there.
Sorry. It should be 2 cross 1. Correct. So it is 2 cross 1. Yeah. So what are independent variables and dependent variables here? So as I have said earlier, this pivot element will basically your dependent variable, and at which column there are no pivot element, that will give you free
X3
variable or independent variable.
x3 is free variable, sir.
So x3 is free
And
and
x1
x1 and
is
x2 are dependent.
dependent.
Right?
Okay. Yeah.
Dependent. Okay. So this we already know. Now how these dependent variable are depending on the free variable. So if you solve this equation, so x1 is your minus x3 and x2 is your x3.
Yes.
Right?
Yeah.
So if we want to write it as a set, so we want to write null space of A, right? As a description. So this is x1, x2, x3 such that ax so let me write it as x. So ax equal to 0. That is basically the definition. Now we have calculated that this x3, x1 and x2 are dependent on x3. So I can write it as x3 such that x3 is in R. Correct? This will be my null space. Right?
Yes.
So how many? So if now I want to give you a basis of this null space, what will be a basis? Can you give me a basis of this null space?
Minus 1, 1.
1.
Exactly. Basis of null space of A is, so one basis, basically there can be many bases. So one basis is you put your free variable as 1. So there is only one free variable. So this will be your basis. So basically the number of free variable will give you the dimension of this null space. So dimension of null space, what is the dimension?
1.
1.
One quantity of this basis. And this is basically your nullity, correct? Now you remember in week, at the end of week 4, we said that this number of dependent variable, okay, that or basically number of non-zero rows here in the row reduced echelon form, that is basically your rank, right?
Yes.
Yes.
Rank of a matrix. So what is rank of this matrix?
2.
2.
2, correct. So now we have started with a 2 cross 3 matrix and we got nullity as 1 and rank as 2. And it is always true that rank plus nullity plus n when A is, if A is and m cross n matrix. Okay, this is called rank nullity theorem. So you don't need to know the proof. Basically, this example will show you the proof, basically, right? Because the number of free variable will correspond to the nullity and number of dependent variable will correspond to the rank, correct?
Sir,
And
sir,
that together, yeah,
sir, I have a question.
yeah.
Sir, to get a basis, can we substitute any value for here x3? Like we have
Yeah. You can substitute any value.
So
you will
there
get
are
infinite number of bases.
Yes.
Yeah, but all the base, I mean, whatever the basis you get, the coordinate will be 1.
Yes, sir. We will get.
So that
We'll
is the
just get
dimension.
one element or one.
Exactly. Any value, not 0. Okay. Don't put 0 because then it will be just 0 vector. That doesn't
Can we
make
take
sense.
minus 2, 1? Sorry, minus 2, 2, and 2?
Anything other than 0.
Other than
Anything other than 0.
Sir, what will happen if we put 0 here?
No, if we put 0, then what is the vector we are getting? Only 0 vector, right?
0 vector.
But whenever a set consisting a 0 vector, is that a linear independent set?
No.
No. So it will not form a basis, right? But we need a basis. That means we need something which is linearly independent. Correct?
Yes.
So that's why we cannot put 0 here. Okay? Clear?
Hello, sir.
Yeah.
Sir, we have used same method for finding rank and dimension of vector space, basis of vector space. So is it related to that also? Suppose we
Related
find
to what?
suppose we want to find like basis of a vector space.
I mean, basis of vector space, I mean, this is a part of that, right? Here
okay,
also we are calculating basis of a vector space. And what is your vector space? This is the vector space you are talking about.
This is the vector. That's why this.
Okay. Yeah, exactly. That's why the procedure is basically the same, whatever we are doing. We are basically finding some dimension of a vector space.
Okay, sir.
Right? But this is a specific vector space, which is called null space.
Null space, okay, sir.
Okay? Clear?
Okay, sir.
Yeah.
May I ask a question?
Yeah, sure.
Sir, would you be discussing the linear transformations?
Yeah, I will. So in week 5, only linear transformation has just started, right? Only the definition is given. Right? So in week 6, we have to discuss it little bit in detail.
Sir, may I ask my doubt?
We are not able to understand. I
Which
think
one?
that only the starting part of linear transformation I am not.
I will
How I
discuss
will deal.
I will discuss. Yeah.
Sir, I have a question.
Yeah,
Actually, sir, we have problem in finding out whether it is 1 1 on 2 or what would be the.
I will discuss
that concept is weak, sir.
Okay,
Sir, my
sure.
doubt is related to null space.
Yeah, go ahead.
Sir, what does rank and nullity geometrically or graphically mean?
Okay. By seeing this, can you, I mean, yourself, can you see that what is the geometric meaning of these two? Any idea? So when we are talking about 2 × 3 matrix, so you are in R3, right?
Yes.
Now, what this null space basically is meaning? What this null space signifies there?
I'm not getting it.
First of all, this part is clear, right? You are dealing inside R3, right? For this example.
Yes.
Yeah. So we have started with a 2 × 3 matrix. So we are dealing inside R3. Now we are talking about a particular space, which is depending on this A and giving us this. So basically the solution space of this equation, correct? And we have
Yes.
calculated that this is a one-dimensional vector space. And how it is look like? This is basically this, right? X3 minus X3, 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 right? So basically, if we write in terms of T as a parameter, so if you vary T, you will get this subspace. This will be a straight line inside R3, right? So
Yes.
if you apply your matrix on this, any point on this line, that will give you zero vector. Okay. Is it clear?
Yes, and sir, rank?
Rank is basically, okay, I should not say rank now. So if I discuss linear transformation, then I come to rank, then it will be okay?
Sir, sorry to interrupt you, sir. Can you please explain this minus T, comma T again, please?
I mean, I have just replaced X3 with T. Nothing I have done. Okay.
Yes. Graphically, what does it mean, sir?
It is a straight line. It is a straight line. Right? Because it is a one-dimensional thing. And what is one-dimensional subspaces inside R3? That are straight lines.
Sir, two planes are intersecting in a straight line.
Exactly. Two planes are intersecting in a straight line. And this is a straight line passing through origin. Okay. Any one-dimensional subspace inside R3 is basically a straight line passing through origin. Correct? So that is your null space. And rank is basically something different here. What we have defined, rank means number of independent rows, right?
Yes.
Yeah. So if we start with a matrix, like we have started.
So number of dependent rows, right?
So number of
Yes, sir. Number of
non-zero rows.
Number of dependent rows.
Number of number of dependent variable, that is different. Independent rows.
Dependent
so
column.
what is it? No, independent column, that is the same thing.
Okay, sir.
So yeah, so let me explain that what rank is. Okay, let me explain this. I thought this is already discussed in your last session. So you have seen this row space. What is row space?
Taking vector as a row, sir.
So in this matrix, there are two rows, right? A11, A12, A13. This is one row. A21, A22, A23. That is your second row, right? Take span of this set. Okay, that is your row space of A. Clear? So what you have to do, you have to take the rows as a vector, the rows of the matrix as your vector, and take the span of that set. That will be a vector space, right? We have already seen span of a set is a vector space. So you know what a row space is, right?
Yes.
And dimension of this row space is your rank of it. Is it
Got
clear?
it, sir. Thank you.
Okay.
Excuse
so
me, sir.
basically, okay, 1 minute. Let me just finish this. Then I will take your question.
Sir. Yes, sir.
So basically, this is called row rank. And if you take span of columns, this, then 1, 2, A22, A13, A23. Okay, you take the column. all the column as your vector, take the span of that, that is your column space. Okay, and then if you calculate the dimension of your column space, that is your column rank. Now, we don't have to calculate both of these because there is a theorem which said that row rank and column rank are exactly the same. Same as column rank. And that's why we can define rank of A as any one of these. Is it clear?
Yes, sir. Yes, sir.
Okay, great. Yeah, someone was asking question.
Yes, sir.
Can you
Yeah,
take the
one by
example?
one by one.
Yeah, can you take the one example which have two independent variables?
Two independent. This one has two independent variables, no? Same thing. I will explain this example further.
Two
Okay?
dependent, sir. Sorry, two dependent variables.
These have two independent variables. That's what I am saying. This is rank 2, right?
Yes, yes.
Yeah.
Like x3 is a free variable. Cannot we have like x4 and x5 free variables?
We can have.
Yeah.
We can have.
So how to
in that case, the matrix should be big, no? The matrix should be something cross 5.
Yeah.
Right? Then we have 5 variables. Yeah, I will give you example. Okay? I will give
Sir, even through variables also
For
we
the
can
same
decide
matrix, can we
rank.
write a row?
Sir,
one by one. Yeah.
even through using variables also you can decide rank, no?
Yeah. That's what I have said, no?
But
so here, if you see two dependent variables, so rank is 2, basically. So where your dependent variable is coming from? Coming from the pivot element, right?
yes.
So all those pivot element is basically your non-zero rows after row reduction.
And also you were saying below, can you go down, sir?
Independent row, sir. What is that? Dependent.
I'm not able to understand that statement.
This one.
Here, when you said this, yeah, independent
This
number.
is independent row, not variable. So what if you take a set and you calculate the span of that set, right? If all these element, all these vectors are independent, right? Then what will be the dimension of that vector space after spanning? The number of these variables, right? Number of these vectors.
So it is linearly.
If all these rows are linearly independent, then after spanning with those, you will that set itself forms a basis of the vector space, correct?
Yeah. Yes, sir.
Now, if they are suppose the second vector is dependent on the first vector, I mean this set is not linearly dependent, not linearly independent. Okay. Suppose the second one is dependent on the first one. Okay, second one is scalar multiple of the first one. Then what will be the dimension of the spanning set?
1.
1. Can you understand now what I am saying?
Yeah.
No, sir, I didn't. So please explain the concept of dimension.
Concept of dimension?
Yes,
for
sir.
the same example.
Actually, sir, I just got.
Sir, may I make one submission, please?
Otherwise, we will just round back.
Dimension means it is
Sir, I want to make one submission, sir. Sir, this all has been discussed till week 4, sir.
No, these has not discussed in week 4. This was not in week 4.
Sir, we already know row rank is equal to column rank. I already know this. Till week 4, it has been.
Okay. If someone has confusion, then let me clarify that. Then you know that's better. But let me clarify this, then I will come to this question again. Okay. Yeah. So basically, I am saying, suppose what is you have a matrix like this. Okay. So let me start with the previous one. 1, 0. What was the matrix? 1, 0, 1, 0, 1, minus 1. Okay. This was our matrix. So I am saying my row space. What is row space? Row space is span of these two vectors, right? Correct? Now what is span of these two vectors? Can anyone tell me? What is this space basically?
R3.
If I want to write it as x, y, z.
R3, sir.
R3, sir.
No, this is not R3. How it can be R3? There are two vectors only. R3 has dimension 3.
Yeah.
It is a subspace of R3. That's clear. Right? Because vectors are coming from R3. So basically, how we will calculate the span?
A times 101
1
B times
plus
01
01 minus 1.
Correct. So this is basically A, B, A minus B, right? So all these vectors of this form, right?
Yes.
So basically, if I want to write it as x, y, z, this is where
X comma y
z
comma
equal to x minus y. Correct? Clear? Where x, y, z are coming from real number. Okay, fine. This is my row space. Now, when I am talking about the dimension of the row space, what is the dimension of the row space?
2, sir.
2, sir.
It is clear to everyone? Because there are two free variables, right?
Okay.
That's true.
Two free variables. And if now I want to give you a basis of this vector space, you will give me this basis itself, right?
Yes, sir.
You can give me this basis because these two are linearly independent, correct?
Yes.
These two vectors are linearly independent. This is clear.
Yes, sir.
So that is what I am saying. If you have some set V1, V2, V3, V4, suppose 4 vector, if you calculate the span of this set and all these vectors are linearly independent, if all these are linearly independent, I mean this set is linearly independent, then the dimension of span of this set
It is 4, sir.
4. Exactly. Okay.
So to
similarly
calculate
here these two
dimension, we
set,
have to calculate span first.
you need not calculate that. That's it's my point. If
It's a
you are
independent
spanning
vector.
with those vectors only which are linearly independent, then that
Yes,
is
sir.
your basis, right?
Yes, sir.
Because that is the definition of basis. Linear independent set which span the whole vector space. Now what is the span? Span is your vector space, right? So
Yes,
these
sir.
4 elements will span your whole vector space, and you know these are linearly independent. So the dimension of the cardinality of the basis is basically 4, the number of vectors which you have started with. Correct? Clear?
Yes, sir.
Till this portion it is clear?
Yes,
Yes,
this
sir.
part is
Yes,
clear.
sir.
Yes, sir.
Okay.
I have just
When we
one
go
doubt.
to rank, there is a confusion.
What is the
Dimension
confusion?
is what dimension is. It means the cardinality of the basis.
Yeah, that is the definition.
And sir, here
Right?
free variable and independent variables are same, right? Like, or it is different?
No, now I am not talking about free variable and independent variable.
No, sir,
I
you
am
mentioned.
talking about only vector, independent vector,
No, sir,
independent
you
linear
mentioned.
independent set.
You mentioned, right, sir, dimension of row space is 2 since we have two free variables.
That I
X and
have,
Y.
yeah. So I am creating the relation now because I mean any way you can calculate it, whatever way you can find it. I just pointing out the relation of all this, connection of all these things. Okay.
No, sir, my
So here
question
I
is,
have mentioned the rank is basically number of independent rows. How that makes sense now? That is what I am telling. Okay.
no, sir, I want to
Yes.
calculate dimensions, sir, so I will see the free variables, right, or how it is. That was my question.
Yeah, exactly. But dimension of what you are calculating? You are calculating dimension of the row space basically.
Yeah.
Okay.
Sir, if we calculate dimension of any matrix like 3 into
Dimension
4,
of any
3 into
matrix
5.
does not make sense. That I have mentioned
Okay.
again in week 4. Dimension of matrix means what? What do you mean by dimension of a matrix? We always talk about dimension of a vector space, right?
Okay.
No, I mean this okay does not seem confident. So
Can't we say
what
that
is
number of
dimension
Sir,
of
actually, I
vector space?
just
I mean,
got
what?
confused in this concept of dimension. Sometimes I got correct answer, but sometimes I just got confused.
What is dimension of a vector space?
Row into number of rows or columns.
No, what is the definition of dimension of a vector space? Just tell me
It
that.
is cardinality of
Cardinality of the basis. I knew this.
Cardinality of the basis. So you have,
Yes.
first of all, you have to find what your vector space is. Then you have to
Yes,
calculate
sir.
the basis. Find the cardinality of the
Okay.
basis. That is your dimension. There is one and only one definition of dimension. Okay?
Okay. Okay, sir.
Clear?
Yes, sir.
Is it
dimension
clear?
of matrix? Can't we say the number of free variables?
Dimension of a matrix does not make any sense. Dimension of a vector space makes sense. Dimension of a matrix means what? Nothing. I mean, you are given a matrix, so what is the dimension of that? I mean, there is no point of dimension in that. You have to find your space for which you are calculating the dimension. A matrix does not form a space. Correct?
So if we like in statement question, if we get matrix and then they are asking about the dimension of the vector space, then we have to calculate the basis
what?
of that matrix.
Yeah, no basis of that matrix. I mean, no.
Then
I mean, where have you find this question that you are given a matrix and you have to calculate the dimension
no,
of that
sir,
matrix?
that was statement question, and by that statement we are getting matrix. That's why I'm asking this.
So if you see in your in our last live sessions, I don't know whether
Yes,
you were
sir.
there or not. So suppose I am calculating this, I am defining a vector space like this. These are coming from 2 cross 3 matrix. Okay. Okay. So this will form a vector space, right?
Yes, sir.
Can you tell me what is the dimension of this vector space? Can you tell me what is the dimension of this vector space?
Wait, sir.
Here I am not talking about any particular matrix, right? Here I am taking
Yes,
a set of all the matrices, 2 cross 3 matrices, right?
Yes, sir.
This will form a vector space with usual addition, matrix addition, and scalar multiplication. Now I can calculate the dimension of this vector space.
So then 2.
At least 2.
Dimension will be 2.
Why?
Maybe 2. At
Why?
least 2.
Why?
Because there are 2 rows and 3 columns.
3.
Is it?
Dimension would be 3, sir.
How many free variables are there?
3.
6. 6.
Okay, dimension is 6. Yes. Yes.
Right?
Forget it.
So this is the matrix, right?
Yes, sir.
This is any particulars. This is any general matrix of this set.
Yeah.
Right?
Yeah.
General matrix of this set. Okay? Now, what is your basis? I mean, if you have to give a basis, what you will give?
A11, 0, 0,
Yes, sir.
Instead of
0,
linear
1.
independent
Yes, sir.
vectors.
Matrices would be there.
Is it clear?
Yes, sir.
Everyone?
0, 1, 0.
Yes,
Can I
sir.
ask one question here? Can I ask one question here?
Yeah.
If
Go ahead.
A11 is equal to A23, then it will be 5, isn't it?
Yeah, exactly.
Yes.
If there are some condition, then it will depend on that.
Okay.
Sir, I'm confused between this free variable you are calling, right, sir? So it is not, it is different from this dependent variable and independent
No,
variable.
same thing.
Yeah, okay. So I
Same
think
thing.
free variable is the independent variable, right, sir?
Free variable means here, I mean, I am talking about how many elements are free here. You can put any value here, right? And that will be a matrix in this set, correct?
Yes.
You can take any value for this 6 element, which will give you a matrix in this set, correct? Is that correct?
Yeah. Yes.
As you can take any element, any real number for these values, that is what I am calling, these are basically your free element. You can choose any values for those.
Okay. Yeah, got it.
Okay.
Thanks.
So there are 6 free things. No one is dependent on anyone.
Yeah, got
right?
it.
So the basis, if you want to make a basis of, I mean, calculate a basis, give a basis of this vector space, you need 6 elements to do that, right? So the cardinality of the basis will be 6. So the dimension of this space is 6. Correct?
Yes, sir.
Now I am taking any particular element of
Even
this.
the rank will be 0, sir.
No, 1 minute. Now I am taking any rank of what?
Rank of this matrix. I mean,
this is infinite. There are infinitely many matrices here.
yes.
This is not a single matrix. This is a set of matrices. There are infinitely many matrices.
Yes, infinite number of values it will take.
So, I mean, when you are talking about rank of a matrix, you have to give me a particular matrix, no?
Okay.
That's why I am saying this rank and dimension of vector space, these two are different things.
Okay, sir. Now.
Okay. That is what I was trying to convey in earlier live sessions also. Now I am taking any particular matrix from this set. Okay. So this matrix, if I take this matrix B, will this matrix be inside this vector space?
Yes.
Yes.
I am giving a particular matrix. Now I can talk about rank of B. Not that has nothing to do with the whole vector space. Okay. What will be the rank of B?
It is 2.
2. Correct? How you are calculating it?
Because 2 dependent variables.
Number of non-zero rows.
Number of
anything. There are 2 ways you can calculate it. What you have already seen. That is after doing row reduction, which is already this matrix is in row reduced form. So the number of non-zero rows will be your rank. Or else, if you see the pivot element, the same thing, that will give you the number of dependent variable. That is your rank. So both of these are equal. Same thing. Whatever you think you are comfortable with, you remember that and do that. Okay. No issues with that. Is it clear?
Yes.
Okay. Now what I was saying, the number of independent rows in a matrix. What I was saying that, see, if you take these 2 rows, one is 1, 0, 1, another is 0, 1, minus 1. If you take these 2 vectors, these 2 elements as a vector, and you calculate the span of this, which I have calculated earlier here, right? This is your row space, correct?
Okay, sir.
That is a vector space, correct? Row space is a vector space. And so this also has a basis. Now, if we calculate the dimension of this vector space, that will be also 2, because these 2 vectors which I have started with, that is also linearly independent, correct? Now, if suppose I am taking another matrix, say 1, 0, 1, 2, 0, 2. This is another matrix in that same vector space, correct? This C also belongs to V, right?
Yes, sir.
Okay. Now, if I want to calculate you the rank of this, what you will give?
It is 1, sir. Because second one is dependent on the first.
Exactly. So basically, this is the number of independent rows, correct? That is also one definition of rank.
Okay, so now I got it. Why you have written that independent rows above this?
Exactly. Exactly.
Okay. Now I understand.
What I was doing. Now, if you calculate. Now, if you take these 2 elements as your vectors, this is your row space of A, right? Now, can you tell me what is the dimension of this row space?
1.
Is it clear to everyone?
Yes, sir.
Because this is already spanned by this. So we can ignore it basically. This is linearly dependent. So only one element will be there. So this is basically span of this thing, right?
Yeah.
So how many number of rows are there? That is enough to calculate the rank of this. So dimension of this row space is basically 1, which is rank of A. Not A, I have given it C. So let me write it as C.
So, sir, we need to see the number of independent rows, right? That is
Sir, even the dimension is also
we can say
right?
it is a fundamental row.
Whatever you want to call it. I am not giving any name to that. Okay. Just remember number of non-zero rows. Okay. That is basically the thing we are calculating via rank. So someone was asking the geometrical representation or what is the significance of rank. That is the significance. So you take all the rows as a vectors, take the spanning set, that will give you a subspace of some, suppose we are calculating for M cross N, that will be a subspace of Rn. Now, among this set, how many independent vectors are there? Okay, in that set. So that will give me the dimension of the vector space, the subspace, or dimension of the row space. That is basically the rank.
We can also see by variables also, no, sir?
Yeah. That's what I have said earlier. No, you can do whatever you want. I am just giving you the significance.
Okay, sir.
Okay. You can do the same thing. You are given this matrix. What you will do? You will do row reduction, right? So R2 minus 2 R1. So you will get 0, 0, 0. Now only one pivot element, right? So how many dependent variable will be there?
One.
Only one.
One, sir.
Only one, right? Because there are only one pivot element. So number of dependent variable is your rank. There, so rank is 1. You will get to the same place. Okay. Now someone want to see how many non-zero rows in row reduced echelon form. This is your row reduced echelon form, right? How many non-zero rows are there?
One.
So rank is 1. Whatever way you will do, you will get down to the same place. Is it clear?
Yeah, sir. I have one doubt, sir.
Yeah.
In previous example, where you are saying, right, infinite matrices would be there, right, sir?
That is the vector space.
Yeah. In same case, sir, there will be infinite vector spaces also, right, in that matrix, sir.
In that matrix, there will be vector space.
No, sir. A belongs to matrix 2 cross 3, right, sir? So there in that for that matrix, sir, only that vector, like the vector space belonging to this matrix,
vector space. No. This is the vector space. I mean, vector space consists of all the matrices of 2 cross 3.
Yeah, sir. So again, sir, the vector space is consisting of that matrices, right, sir?
Right.
And this matrix is infinite, right?
There are infinite number of matrices.
So ideally, then this vector space will be also infinite, right, sir? Because it is belonging to that those whatever you saying matrices, right?
I am not sure what you are asking. Are you asking whether the cardinality of this vector space is infinite?
Yeah, sir. That was
any cardinality. I mean, any non-zero vector space has infinite cardinality.
So my question actually was that, sir, you mentioned this basis, right? 1, 0, 0. This all are in the matrices form, right? These are the vector space, right? So
this is the basis of the vector space. This is basis of V.
Yes, sir. This is basis, but the vector space will be in which form, sir? Like if you are writing just the vector space, it will be in any of these forms, right? Yeah, sir. So,
No, not any of these forms. This is the vector space. All 2 cross 3 matrices.
So yeah, that was my question, sir. Again, it is going round and round. Like if matrices are infinite, right, and this vector space
matrices are infinite mean what?
Like we can have any number of this such matrices, right? M2 cross 3, sir, right? And this vector space is belonging to the form of that matrices, right?
Vector space does not belong. All these matrices, this vector space consists of all such matrices.
Okay.
Vector space is the set. I mean, take it as a container, okay? Take it as a container where all these matrices are there. Okay. All these 2 cross 3 matrices are there. This container is basically your vector space.
Okay.
It has infinitely many such matrices. Is it clear?
Yes, sir.
Okay. So, where are we? Yeah. So, this part is clear to everyone? Any doubt till this point you can ask. Because every term we are seeing the same kind of confusion. So, we know this place is little bit confusing for all of you. But
Sir,
at least for now, is it clear?
Sir, so we can say dimension and the ranking is same.
No, don't make this kind of
Only
statement.
for vector space.
Okay, then again we will go round and round. You know what is rank of a matrix?
Same.
Yeah.
Don't make also that kind of statement. They are not same. You know what is rank of a matrix?
It's a non-zero rows.
After row reduction.
Matrix. Yes, after row reduction. Yes.
Correct. So you know what is rank of a matrix. You know what is dimension of a vector space?
Dimension is like how many free variables.
Cardinality of basis.
Like cardinality.
Cardinality of the basis.
Cardinality of basis.
Basis.
Only
It's
cardinality.
like
That's
how
right.
many independent variable we have. That is the dimension.
Sir,
No.
in one of the video lectures, sir had
So
mentioned that
independent
if you are
variable is not a case of dimension of vectors, no? Independent and dependent only used for matrix rank for rank
No.
only.
Independent and free variables, free element you are talking about.
Yes.
But don't confuse it with when I am calculating the nullity or rank. Okay, these are two different things. These are two different
That's why.
contexts in which I am using this term. Okay.
Nullity and dimensions are same.
Dimension. So if you know a vector space, you have a vector space. You have to give me a basis. The cardinality of that basis is your dimension.
Yeah,
Okay?
and
Yes.
same is nullity.
Nullity is also a dimension.
Yeah.
Dimension of the null space, right?
Yeah.
Clear?
Yeah.
But sir, when we use independent variable and dependent variable only for matrices, na? For rank and nullity.
For rank and only for not that case. For finding rank and nullity, you are using that concept of dependent and independent variable because you are dealing with a set of
Row
linear
equation.
right?
Yeah.
Set of linear equations. Whenever you are dealing with set of linear equation in any context, you can use that. That terminology. That is a terminology, right?
That is
So
terminology.
if it has connection with any other aspect, you can use it there, right?
Sir, I think, can you give him a small example, sir, where you are calculating the independent variable and the dimension and the rank, sir, in just a very simple example. And
This
the
is what
dimension
I
and
have
rank,
done here, right?
dimension and rank should be different, sir. That was actually my question.
Sir, everyone is
this is the
confused
place
between
what
these
I
two.
again.
Sir, so we
Okay.
can say rank and dimension of the row space.
Rank is dimension of the row space, exactly.
Yeah.
Exactly. Okay, see. I am taking set of 2 cross 2 matrices, okay? So my vector space is M 2 cross, say 3 cross 3, let's say. R. Okay, so this is my vector space. Okay, now if I want you to find the dimension of this vector space, what is this dimension?
9.
Would be
Is it clear to everyone?
9, sir.
9?
9.
Would be
Everyone?
maximum 9.
Yes, sir.
Yes, sir. 9.
What a maximum 9? I mean, dimension is fixed, right? So can you give me a basis of this?
Yes, sir.
Sir, 0, 0, 1, 0, 0.
1, 0, 0.
This kind of thing, right?
0, 0,
So at
So
each
keep on
position
shifting
there will be
1.
one, and so like that there will be 9 elements, right? So this dimension is 9. Is it clear?
Yes, sir.
Yes,
Yeah,
sir.
sir.
Fine. Now I am giving you a particular element of this vector space. Okay. So this is a particular element of this vector space, right? A belongs to V. Correct?
Yes, sir.
Correct? Is it clear to everyone that this matrix belongs to this M3 cross 3R?
Yes.
Everyone?
Yeah. Yeah.
Yes,
Okay.
sir.
It takes its own.
Now I want you to calculate rank of A. What is rank of A? How you will
Row
calculate?
reduction.
Row
Row
reduction. Good.
reduction.
So do row reduction. What is the first step?
3 times.
R3
R3
minus 3R1.
Okay, great.
R3 minus 3R1.
Great. So this is 0. And what is this?
Minus 1.
2.
2.
Oh, yeah. Minus 2.
Rank will be 2.
2.
Minus 2.
8 minus
Only 1.
Then
1. 1. 3, 0, 0.
0, 0, 0.
Okay. Then what is the second step?
R2
minus
Divided by 2. Yes.
and we do R2 minus R3 directly.
But I am following the standard process. Okay, you can do anything, but I am following the standard one. Okay. So then
R2
R3
R3 minus
R2.
Twice of R2.
okay. Then
we have the rank.
then another one step is remaining, no?
Yes.
R1 minus
R1 minus twice of R2.
Okay. So this is the row reduced echelon form, right?
Yes, sir.
Okay.
Can
How
you
many
scroll
non-zero
somewhat
rows are there?
up, sir?
2.
We could not use the second last matrix.
You can use, but I am using exactly what is row reduced echelon form. That's why you can do from here itself. Okay. Yeah. So number of non-zero rows in the row reduced echelon form is 2. Right? So what is rank of this matrix?
Rank is
2.
2.
Okay, great. Now I want to
Nullity is
find you
1.
the nullity of this matrix.
1.
It is 1, sir.
Nullity is 1.
How you are calculating it?
Number of
Independent columns.
Number
Independent variables.
variable.
Where are your variables?
One third column, sir.
Third column.
Basically, here we have one pivot, here you have one pivot, there is no pivot, right? In the third column. So number of independent variable will be 1. Right? Clear?
Yes.
That will give you a nullity. Okay?
Hence
Is it
dimension.
clear? Dimension means dimension of what? Dimension of the vector space already you have calculated. It is 9.
Yeah.
Clear? It is clear to everyone?
Yes.
Yes.
Yes, sir. Yes, sir.
Excuse me, sir.
Fine. Yeah.
Yes, sir. Clear, sir. Clear.
There was
Okay,
a
great.
matrix like this where it was a 3x3 matrix, but the second element of first row was only 1 and everything else was 0.
Okay.
There I got confused. So it will be like only x2, right?
What is your matrix?
3x3 all are 0 except 1 2 element. The second element
Except
of
1
first
2
row.
element. This one?
Yes, sir. Yes, sir. And rest everything is 0.
So what is the rank of this matrix?
1.
1.
Rank is 1, right?
Nullity 2.
Nullity is 2.
Why?
So like how will
The
we
nullity
write
should be
this?
3.
No, need 2 because
2. Yes, sir. It would be 2.
two
Why?
independent variables, sir. Two
x1,
independent.
x3.
Two free variables.
First column and third
One
column.
dependent.
So basically this element, now this is at the, so I can do a row operation, R1 and R2 interchange, right? Now this will work as a pivot element, correct?
Yeah.
Yes.
So that is your pivot element, which is for the dependent variable. And there is no pivot element in the first one, there is no pivot element in the third column. That's why there are 2 independent variables. That's why nullity is 2. Is it clear?
So how will we write this in the form of that null space set type? x1, x2.
How you will write it? So whatever it is given, you take x1, x2, x3, correct?
But actually this was not given. This I found after reduction. Given was the first was 1 and below it was -1.
Okay, but we need this one. No, after reduction you got it, then we can calculate the nullity space from here itself, right?
Yes, sir.
So what is this? You are getting just x2 equal to 0. So this is basically your fixed thing, correct?
Right.
The second one is your fixed thing.
Yes.
Okay.
x2
So your variable will be x1. This is your 0, x3. x1, x3 can take any real numbers, right? This is your null space, correct?
x1, 0, x3. Okay.
This is your A. So this is your null space, correct?
Yes.
Is it clear? This is your null space.
Yeah. Yes.
Okay. Now what is the dimension of the null space?
I kept doing 0, x2,
Null
0.
space 1.
No, why 0? I mean, at second x2 you are getting 0, no?
X2 is 0. Okay.
X2 is dependent. Other are independent.
So what is the dimension of this null space? 2.
1, sir.
2.
1.
How?
2 independent variable. 2 free
Okay, sir.
variable, no? Just now you have said there are 2 free
Okay.
variables. Okay. So null space, that is your nullity, no?
Okay.
But
Yeah.
hello, sir.
Yeah.
Earlier you said that nullity nullity equals to dimensions. That is true for vector space or matrix or both.
Nullity equals dimension of?
Yes,
I have
that I
written
saw.
dimension of?
Yes, yes.
Here, tell me dimension of?
Dimension of A or dimensionality of A, both are same. So is it true
No,
for
what is
matrix?
nullity? First tell me what is nullity.
Number of independent columns.
No, I want the definition.
Cardinality
That is the
of
process you
number
will
of
find
bases.
nullity, but I want the definition of nullity. What is
Cardinality of
cardinality
bases.
of null
Cardinality
space.
of basis of null space.
Exactly. Dimension of null space, basically. Right?
Yes, yes.
Okay.
Dimension of null space. Okay?
May I ask a question here?
No, let him finish the question. I mean,
Sure.
yeah.
Okay, sir. I thought that nullity.
I mean, is your doubt clear or
Yeah, sir. Yeah.
should we go ahead?
Yes, sir.
Sir,
Okay,
what is basis
great.
of this null space, sir? Basis 1 0
You tell me now.
1
Yes,
0
sir. Similar
0
question in practice
0 1.
assignment.
First of all, put x3 equal to 0, then put x1
This
equal
is
to
the
0.
basis. Yeah.
That's why
correct.
dimension is 2. Okay.
Exactly. Exactly.
But
Okay.
how did you get x2 is equal to 0 in this one?
Yeah, by
Because we have two
solving this
independents.
equation.
First
Okay,
put one
okay.
dependent
Okay.
0.
Already
By
given.
solving this
Got
equation,
it.
just okay. Yeah.
Got it. Mistake. Yep, got it.
Yeah. Any other
Sir,
doubt till this point?
sir, practice assignment 5.
You solve it. I will not solve that.
No, sir, doubt from that.
Sir, actually,
what is your doubt from that?
Question number 2. I just want to confirm my basis of space, vector space. Null space, sorry.
What is the given?
Given are 4 means we have to derive equations from the given data and find basis of the null space.
Okay. Then you know how to find it, right?
Yes, but I just want to confirm my answer because
I mean, you want me to solve that now? It will be just, I mean, wasting time probably, no?
okay, sir, no problem.
So, is the solution uploaded there?
No,
No,
not
sir.
yet.
Not yet?
No.
Okay. So, tonight I will upload it. You can check it from there. Will that
Okay.
be good?
Okay. Okay.
Okay.
Yes.
Because, I mean, solving those equations will be just waste of time. Okay.
Okay, sir.
Okay.
I want to discuss the concept properly so that you can do it yourself. That is basically my idea. Yeah.
sir, can you please discuss the linear transformations and how to check whether they are linear
I am
transformations?
going to that. But before that, please confirm whether this nullity and rank, these are clear or not.
Yes, sir.
Because
Yes.
again in week 6, we are coming back to the same place. I am saying it.
Now it is clear, sir.
Now it's
Yeah,
clear.
no?
Yes, sir.
So when I will discuss the nullity and rank for the transformation, then you will not ask me the same question, right?
Yes.
All of
No
you are
problem.
promising me?
No problem.
Yes, sir.
Just kidding.
Okay. Okay, great. So now, one of you just tell me, so let me pick any one of you who can tell me just summarize what I have said till now. What is rank, what is nullity, what is row space, what is column space, what is basis, everything. Any one of you can summarize it in a little?
Sir, you write the terms and we will then explain.
Okay. So, give me a minute, okay? Give me a minute. Yeah. So what we need basically, we need basis of a vector space. That is the first point. Then we need what is null space. Then we need what is row space. Then we need what is rank, say row rank, which is eventually rank. And then we need what is nullity. We need all this thing. So can you just tell me one by one? Anyone who want to
Sir,
contribute?
basis is the minimum spanning set which spans whole of the vector space.
Exactly. Or in terms of linear independence set?
Maximum linear.
Maximum linearly
independent set.
Or
Exactly.
minimum spanning set.
Minimal spanning set or maximal spanning linear independent set. Okay.
Yes.
Okay. Fine. And what is your null space?
So null space is the solution, is the set of solutions which satisfies the homogeneous Ax is equal to 0.
Exactly. So suppose you are given any matrix A, then Ax equal to 0. If you calculate the solution space of that, that is your null space. Correct?
Null space.
So remember, null space is a vector space. Correct?
Yes, sir.
So this you know already. So minimal spanning set or maximal, anyone you can use, linear independent set, and cardinality of it called basis, right? Cardinality of basis is called dimension. Okay, great. Null space of a matrix.
So this is also equal to rank. Cardinality of basis is the rank finally.
Again, you are creating same kind of discussion. No, that is not true. Cardinality of basis is not rank. Rank of a matrix is defined.
Dimension.
That is dimension. Don't use rank in here. Sarah
Yes,
used
sir, yes, sir.
both
It's
the terminology,
dimension.
but that is confusing. So we are avoiding the rank here. Okay.
Okay.
Okay. So null space is basically X such that Ax equal to 0. Correct?
If homogeneous.
So if A is M cross N matrix, then this is a subspace of
Rn.
Correct?
Okay.
Subspace checking we have done, right? Okay, great. Now what is row space of a span of row
independent
vectors?
row.
Span of row vectors. Yeah. I mean, if you take span of all the row vectors, then eventually it comes to the independent rows, right? Because the dependent is always in the span. I mean, you can delete those. Correct?
Yes.
Okay. Now, what is row rank?
Number of independent rows.
Dimension of
number of independent
dimension
rows.
of row
Exactly.
space.
Dimension of
Number of non-zero rows.
So same thing you can call dimension of row space. Someone has mentioned that. Row space of a number of
dependent
non-zero rows. That is basically the dependent variable, right?
Yeah.
After row reduction. So all these are same thing, correct? So this is basically number of dependent variable, if you want to remember in that language. Okay, clear?
Okay.
Yes.
Okay. What is nullity of a?
Dimension of null space.
Dimension of null space. Then
number of
independent variables.
Independent
variables.
Sorry, dependent
Number
variable.
of independent variables.
Number of
Independent
variables.
Independent variables. So this is basically coming when row reduction, after row reduction, right? Row reduce echelon form. Okay.
Excuse me, sir.
Yeah.
Sir, in week 4, before or maybe like when there were questions like what is the maximum possible rank, then that was like asking what is the nullity, like similar sense was there, right? Or different?
No, similar sense.
Like if
so if
maximum
you
possible.
Yes, so suppose you have a 2 cross 3 matrix, then what is the maximum possible rank?
2
Can you tell me? 2, right?
Two. Number of rows there.
Okay. If I have a 3 cross 2 matrix, what is the maximum possible rank?
At least 3.
3.
No, 2. Can you tell me why?
Okay,
Because
three
there
columns
are
Yes, when we are reduced row
pivot must be
echelon
there.
form.
For multiplication with the variables, the number of columns of first have to be equal to number of rows of second, and our solution has, yes sir. So the solution set would be 2 cross 1.
That doesn't matter. I mean, I have mentioned, I don't know whether you have paid attention or not there. There is something called column space also, right?
Yes.
As row space. And at that place, I have said that row rank and column rank are always same. Now, if you go by column, how many columns are there? 2, right?
2
So
columns
maximum column rank can be 2.
pivot.
Right? And
Yes.
as row rank and column rank has to be same. So what is the maximum rank? It can maximum up to
Must be 2.
So basically, it is the maximum of row and column, number of row and column, right? That is the maximum possible rank. Clear?
Okay.
Everyone?
So the rank will be 2.
Maximum rank will be 2.
Yeah, okay. Maximum rank will be 2.
Maximum rank will be 2. Yeah.
All right. Can you
Clear?
wait for a here for a while, sir? Just here.
Yeah. So this is basically what you need to know for rank and null space, nullity, rank and nullity of a matrix. Okay. So I will upload this PDF, then you can basically check this. Okay. Should we move ahead to the linear transformation? So only linear transformation part is remaining.
Yes, remaining.
Okay. So you go through it. Okay. It at the first time it seems little bit confusing because you are doing it the first time. But once you get the connections, how all these things are connected throughout the weeks, then you can get a feel for these topics. Okay? And it will be really useful. I am saying it is really important. Okay. I should mute everyone probably now. Okay. So let me move to linear transformation. Okay, so you know what a mapping is, right? In Maths 1, we have seen that. Correct?
Yes.
Yes, sir.
Mapping or function, basically. So you are giving some input and you are getting some output. And for one input, you cannot have two output, right? That was the definition of the function.
Yes.
And it has to define throughout the domain. For all the domain, all the points in the domain, you have to get some output. Okay. Now, linear transformation, first of all, remember it is a mapping. But it is a mapping from one vector space to another vector space. So on the both sides, for the domain and codomain, we have vector spaces. Correct? This is the first thing you have to remember. So linear transformation means it is a mapping from one vector space to another vector space. Now, for mapping, we just give some input, taking some input from a set and giving output in another set. But now, when we are dealing with vector space, there is an operation involved, right? Basically, two operations. One is addition, another is scalar multiplication. So, in the mapping, somehow this has to be reflected, right? We have to take care of those, right? So, there are two properties which have to hold. So basically, you are taking some element from V, you are getting some element in W. Both of these are vector space. Now, on both sides, we have some addition and scalar multiplication. So T has to respect that. I mean, whenever I have two elements, V1 and V2, so suppose this is my V, this is my W. I have V1 here. So V1 is going to somewhere here. This is T V1. V2 here. This is going to somewhere here. This is T V2. Now there is some element which is called V1 plus V2, right? Somewhere here. This is suppose V1 plus V2. Now where it will go? It will go somewhere here in W, right?
Yes.
This is T V1 plus V2. Now, V1 plus V2 is sum of this V1 plus V2. Now, there should be some relation between T V1 plus V2 and T V1 and T V2, right? That is the relation we are taking as the first condition. It should be equal. Okay, so if I add this TV1 and TV2, I should end up to the same image here. Okay, this is the first condition. And the second condition is T of CV again. So
Repeat again, sir. First condition.
We have V
Yeah,
here.
yes, sir. Can you repeat first condition once again, sir? Using V and W, sir.
Okay. So let me again draw this a little bit better maybe. So this is your V, this is your W. So I have V1 here, okay? I have V2 here. So this V1 is going to somewhere called TV1. This V2 is going somewhere here, which is called TV2. Now there is some element called V1 plus V2, right? The addition will be inside V. Now where this V1 plus V2 go? This will go to some other element TV1 plus V2. Correct? Because V1 plus V2 is another element. Now there has to be some relation between TV1, TV2 and this new element, right? Where the image of V1 plus V2 is coming. So the first condition is saying this TV1 plus V2 should be equal to TV1 and TV2. That is the first condition. Okay. Similarly, there is something called V. So V is going to some TV inside W. So when I multiply V with some scalar, I am getting CV. Suppose CV is here. Now this CV is mapping to some TCV. Now there should be some relation between these two also. What is this relation? If I multiply C with TV, then I should get the same element. Okay. If these two element conditions satisfied, then the structure is basically preserved somehow. You can feel that, right? Because we are basically taking taking the addition operation to that side, taking the scalar multiplication operation on that side. So that's how we are basically want our mapping to be, right? That's why this is the motivation behind the definition. Okay, is it clear?
So I have a doubt here.
Yeah.
So in the first point, why we are multiplying with T? It's just V1 plus V2, no, sir?
We are not multiplying. This is the mapping. We are taking the image of V1 plus V2. I mean, f of x is not multiply x with f, right?
No, sir.
It's a function, right?
It's a function.
It is a function.
This is the input. This V1 plus V2 is the input inside this function.
Okay, sir.
Getting some output V1 plus V2.
T is a function. Yes.
That's what I started with. T is a mapping. T is a mapping. Okay? Which respect these two operations.
Thank you.
Clear? Let me give you example, then it will be little more clear.
Okay. So a operation will be hold, then it will be called a linear transformation.
Exactly. If these two property will be whole, then it will be called a linear transformation. Okay.
Okay, sir.
Okay. So T, say R2 to R2. Let's take some. Both of these are vector space R2 and R2 with usual addition and scalar multiplication. So suppose I am defining at T of x comma y as 2x plus 5y comma x minus y. Okay, I can define it like that.
Sir, can you pause for a moment? I want to ask a question here. Sir, we are talking only about vector spaces here. We are not taking any subspaces or anything like that. In such
subspace is a vector space, no?
Yes, sir. I know that.
So we can talk about that. Why not? I have written V and W, any vector space. Any vector space, any. I can deal with subspace of R2 also. I can deal with subspace of R3 also.
Yeah, and we have the same condition for the like subspace also.
Anything, any vector, it must be vector space. That's the point. Okay? We are talking about mapping between vector spaces. Okay?
So null space is also vector space.
Null space is also vector space.
And here we can also count the null space here.
Don't overthink it now, okay? Because null space will come later, okay?
Okay, sir.
Don't overthink it now. You will get confused, okay?
Yes.
Okay. First, understand what is the definition of transformation. Then we will do variation of example, okay?
Yes.
Now, my question is it a linear transformation? So what we have to check first of all? I have to take V1 as x1, y1. V2 is my x2, y2, correct? What is V1 plus V2? So TV1 is 2x1 plus 5y1, x1 minus y1. What is TV2? 2x2 plus 5y2, x2 minus y2. Now what is V1 plus V2? x1 plus x2, y1 plus y2. I hope everybody is following me. Okay. T v1 plus v2 is t of this x1 plus x2, y1 plus y2. Now this is my x, this is my y. So what will be the image? 2x1 plus x2 plus 5y1 plus y2, x1 plus x2 minus y1 plus y2. So if we break it down, 2x1 plus 2x2, 5y1 plus 5y2, x1 plus x2 minus y1 minus y2. Now, is this and sum of these two will be same?
Yes, sir.
Yes.
Is TV1 plus V2 is same as TV1
yes,
plus
sir.
TV2?
It is same, sir.
It is same, right? If you add coordinate wise, this is 2x1 plus 5y1 plus 2x2 plus 5y2, which is the first one. x1 minus y2 plus x2 minus y2, which is the second one. Correct? So it is, answer is yes. So the first condition is satisfied. Correct? Is it clear to everyone?
Yes.
Okay. Now for the second condition, will it be satisfied? So V is your xy. So CV is CX, CY, right? Okay. So what is TV? 2x plus 5y, x minus y. What is T of CV?
2cx.
2cx plus 5cy.
5cy.
Then
cx minus cy.
cx minus cy.
Great. Now is it this? Is this two equal?
Yes.
Yes, sir.
If you multiply C with that, we will get the second one, right? So it is.
Yes.
So both the conditions are satisfied, correct?
Yeah.
So this is a linear transformation, what I have started with. Okay? Clear? At least
Yes, sir.
definition and example of linear transformation is clear?
Yes. Slightly.
Okay. Now my question is, yeah.
Sir, can you scroll down, sir?
Okay. Okay. So let me ask a question here. Where does 0 go for a linear transformation? In V there is a 0, right? In both sides there are 0.
It goes to origin in the transform
Not
vector
origin,
space.
say it's 0.
Okay, yes.
Okay.
0 goes to 0, sir.
0 goes to 0. How we can show that?
Because when the linear transformation, this TV1 plus V2 equal to TV1 plus TV2 is equivalent to saying that TV1 equal to 0 implies V1 equal to 0.
Basically, you can use these two properties and show that T of 0 must go to 0. Right? 0 will always go to 0 for a linear transformation. So, if you see, when you have to check some mapping is a linear transformation or not, first thing, it should strike to your head that whether 0 is going to 0 or not. If at the beginning you can see that 0 is not going to 0, then you don't have to check anything else. You can directly say this is not a linear transformation. If 0 is not going to 0. Okay? If 0 is going to 0, then the rest you have to check. Okay? Is it clear?
Sir,
yes.
If you can show it in written form, then it would be more clear, sir. First thing is how we check.
Form. So if suppose this example, okay?
Yes, sir.
What is 0 here? in R2?
0,
0, 0.
Yeah.
Where it is going?
0.
It is going to 2x plus 5y. I mean 2 into 0 plus 5 into 0.
0,
5
0.
minus, sorry, 0 minus 0.
Yes.
So 0
It is going to 0, 0, so it is a linear.
So there is a possibility that it may be a linear transformation. Then you check the other conditions.
So
The two conditions I mentioned.
We can prove it from the first statement also, sir. We can prove it from the first statement.
From there. Yeah.
If we take
from
V1
the
plus
first statement, it is coming.
Yeah. If we take there V1 plus minus V1, and we can use TV1 plus T minus V1. Then we can
you have to
put
use
out
the
the
second
minus.
condition also, right?
Yeah, both condition. Using both
condition you have to use. That's what I have said. You can show that T of 0 is going to 0 by using those conditions, but we don't need the proof actually. The point is, suppose I have given you T R2 to R2, a map like that, x minus y plus 1, x plus y. Suppose I am giving you this. On both sides, I have usual scalar addition and usual vector addition and scalar multiplication. Okay. So, is it a linear transformation?
No, sir. Because it is not going to 0.
By just seeing 0, 0, I am saying it is coming to 1, 0, then it is not the origin. Right?
Yes, sir.
Because for R2, origin is the 0 element with respect to usual addition and scalar multiplication. Correct?
Yes, sir.
Correct? So, it is not a linear transformation. Okay. So, this is the first thing. Second thing, which I am stating now, whenever I am talking about a map from Rn to Rn, or the usual vector spaces which we are talking about, okay, it will be subspace of all these things, Rn, Rm. All this coordinate should have degree 1. Okay. What does it mean? Suppose I am taking R2 to R3. Okay. I am giving you a map. Suppose I am mentioning it like this: x square plus y, x minus y, and x plus y. This. Will this be a linear transformation? No. Because there is a power 2. This cannot happen. Okay. Whatever that is, so if in general, if I am writing from Rn to Rn as t, then the linear transformation should be like, so here I have n coordinate, here I should have m coordinate, and it should be a linear combination of this element. So first coordinate should be look like this. Second coordinate should be look like this. I mean, all this variable, all these coordinates, they should have power 1, at most 1 or 0. Okay. Is it making sense?
Yes, sir.
It should be a linear combination basically, because I mean, if you know the name linear transformation, that's why the name came from. The combination should be linear. It cannot be quadratic or cubic, nothing. Okay.
Sir, but if we put it 0 here, then what can we say about this?
That can happen, no? I am coming to that. So I am saying a general form should be like this. It can happen that every element is going to 0. That can also happen. That is called zero transformation. Every element is going to 0 means what? All these AIs are 0 basically. Everywhere.
Sir, from here we can conclude that we cannot check whether the given vector space is a linear transformation by putting 0 every time.
Then vector space is a linear transformation.
Yeah, sir.
Given map. Given map is a linear transformation or not, right?
Yes, sir.
Now, what is your question?
My question is, sir, putting 0 every time we cannot check whether the given vector or a subspace is a linear transformation. A vector can be a linear
subspace is not a transformation. I mean, how a subspace can be transformation? Or how a vector space can be transformation? Transformation means a mapping, right? From one vector space to another vector space. You are checking whether the transformation is linear transformation or not, right?
Sir, any vector,
why vector
any vector in a subspace can be written as the linear transformation of the basis vector. So that is also
no linear combination. You are confused with linear combination and transformation.
Okay, sir.
Okay, so linear transformation is mapping one vector space to another. Okay.
Okay, sir. So can we check for the linear transformation in whether this is a linear transformation or not by putting 0?
What I have said just 2 minutes ago.
What, sir?
Can you recall that? What I have said here? When I was talking about the definition, what I have said, can you recall that? You try. If you go wrong, I will tell. You try. What we have to check when we have to check something is linear transformation or not? What we have to check?
These two properties, sir. T1 plus D2. Yeah.
So before going there, I said that first check whether 0 is going to 0 or not. Okay. If 0 is not going to 0, then it cannot be linear transformation. You don't have to go to the checking of these two properties, right? But if 0 is going to 0, then also there is a possibility that it cannot be a linear transformation. Then you have to check all the two properties. Okay, these two.
And linear transformation is showing the mapping from one vector space to another vector space.
Exactly. Then you have to with these two properties. Okay.
Okay, sir. That should satisfy these two properties.
These two properties should be satisfied. Exactly.
And 0 should go from 0 to 0.
If these two properties satisfied, then 0 must go to 0. Okay. So basically, if you see any transformation like this, I mean all the variables, I mean all the coordinates at degree 1 and all this linear combination are given, you can directly say this is a linear transformation. Suppose I am giving you this. Now you can say it directly. Let it be this. So this is a map from R3 to R2, right?
Yes.
Is it a linear transformation?
Yes.
Yes, right?
Yes,
because the linear combination of these are given only, right? Now you put anything, 2, 5, 7, 9, 18, whatever you like. This is also a linear combination. But you cannot put any power here. That is not allowed. Clear?
Okay. Yes. Powers and roots are not allowed, right?
Anything is not allowed, only degree 1 or 0. Here, what is not there, that is also allowed. Okay? Clear? Suppose I am giving you the same thing like this. X plus 7y. Here only z. Is it a linear transformation?
Yes.
Yes, right? It is also all the powers are 1 or 0. Right? Here x and y are not there, here z is not there. Still it is a linear transformation. Okay? Because it is a linear combination of all these x, y, z, right? At each coordinate. So that is basically the property. So you basically don't have to check even. Right? For this type of example. Right? There are some different type of example where you have to check. That you will find in graded assignment or practice assignment also. But by seeing this, you can tell that whether if this transformation is linear transformation or not, right?
Yes.
Yeah. Clear?
Hello, sir.
Yeah.
Can you tell me? You have said that when first of all we need to check t of 0 equals to 0. So can you tell me logic behind of this? I have doubt.
So I am saying if t is a linear transformation, then these two property has to be satisfied, right?
Yes. Or you have said that t of
1 minute. Now if I am saying if these two property are satisfied, then 0 must go to 0. There is no other chance. 0 cannot go to anywhere else. Okay. So it is better to see whenever you are starting with the transformation, it's better to see whether 0 is going to there or not. 0 or not. If 0 is going to 0, then you come to checking this 1 and 2. If 0 is not going to that, then there is no point of checking 1 and 2 because that will not be satisfied. Right? Clear?
Yes.
Sir,
Yes.
I have a doubt.
Okay. Yeah.
Sir, can you scroll down?
Yeah.
Yes, sir. So you have told that we can have maximum up to 1 power. So if we put 0, sir, the power of x here in the last example you have shown, x to the power 0, then we'll get a constant. Then how it could be a linear
No, 0 means no, not power 0. Sorry, I mean power can be 1 or this coefficient can be 0. I mean there is no z. That is what I am saying. There is not z. Okay, I am not saying this x power 0. I mean then it will be 1. Then 0 is not going to 0. Then it will not be a linear transformation. I am not saying that. I am saying that it can be present. If it is present, it has power 1, or it cannot be
Not
present.
it
That can
will
be
be 0, sir.
happen. Okay, the coefficient can be 0. So maybe for slip of tongue I have said power, but that is not what I meant.
Yes.
Okay, I am saying if it is present, it has power 1. Otherwise, it can be absent. The coefficient can be 0.
Yes, coefficient.
We can have only 1 power, that is 1.
Exactly. Exactly. Okay. Clear?
Yes.
Yes,
okay.
sir.
So this is your linear transformation, the definition of linear transformation. Now, the same, only one thing is left, that is one-to-one linear transformation and onto linear transformation. What are those? So you know what is one-to-one function and onto function?
Yes, sir.
Yes, sir.
Yes.
What is that?
One-to-one means one input, one output.
Yeah.
And onto means one
On
output.
Basically,
onto means for every
this
value
type
in
of
the
situation cannot happen, right?
Yeah.
Yes, sir.
For one-to-one, this cannot happen. Not one-to-one.
But this is onto, sir.
No, I mean, I don't know whether this is onto or not. For onto mean, for every element, we have a pre-image.
Yeah, yes.
Okay. So one-to-one means no two element
have same value or same image.
Go to same image. And onto means this is one-to-one. And onto means every element in the codomain has a
Mastering
p-image.
PMS.
Okay. So this definition works here also. I mean, exactly the same definition. Except mapping, we have linear transformation. Okay.
Can you explain onto with the mapping, sir, in diagram? Like how?
I'm doing that. So R2 to R2, take one example. Okay, this example. Okay. Now, suppose two element. Now my question is it one-to-one? And is it onto? These two questions are there. Okay. So if by definition we have to check. Suppose two element x1, y1 and x2, y2 are going to the same element. Right? We have to show x1 equal to x2 and y1 equal to y2, right? That is the point.
Yes, sir.
For one-to-one. Okay. So basically x1 plus y1, x1 minus y1 equal to x2 plus y2 and x2 minus y2, right? This is what I am getting. So x1 plus y1 equal to x2 plus y2, x1 minus y1 equal to x2 minus y2, correct? Correct? These two we are getting, right? If we add these two equations, what I am getting? 2x1 equal to 2x2.
x1 is equal to x2.
x1 equal to x2, right?
Yes, sir.
And what about the other one? So if we put x1 equal to x2 in the first one, we will get y1 equal to y2.
Y2. Yes. Yes.
So it is one-to-one. So it is one-to-one. So first one is yes. Now what about onto? Any element of here
Sir,
has a
sir, can you
pre-image.
pause? Can you pause for a moment? Sir, while writing transformation t x1 comma y1 equal to t x2 comma y2, you said that the elements x1 and y1 are in the domain, right? And they are mapped to some image, and those images should be these images should be equal to the pre-images.
If this no, I mean I am taking two elements from R2 here from the domain. Okay, these are my two elements.
Okay,
so
sir.
I am assuming if these two elements are going to the same image, can this happen? That is my question, right?
Okay.
So I am assuming let those two elements go to the same image. So these are this is the image of the first one, this is the image of the second one. So I am equating those two images. And by equating, I am seeing that if these two images are equal, then x1 must be equal to x2 and y1 must be equal to y2. That means x1 comma y1 and x2 comma y2 are basically the same element. So we cannot get two different elements in the domain which goes to the same element in the image. That cannot happen. That means it is 1 to 1. Clear?
Yes.
Okay. Great. So this is basically the same thing what we are doing for maths 1. Same thing. Exactly same thing. Now what about onto? How we have to check onto? So take any element from R2, right? Any element of R2 means how it will look like a comma b in R2, right? We should find a pre-image xy such that this happened. Does there exist x comma y in R2 such that this happened? Correct? That is the question. If this exists, then we call it onto, right? Is it clear to everyone?
Yes, sir. Question is clear, sir.
Okay. Now what to do? So anyway, so t of xy, if it has to be a comma b, then t of xy is basically x plus y and x minus y, right? This to be a equal to b. So x plus y should be a, x minus y should be b. Then if we solve this, should I get any solution for x and y? Yes, we get. X is basically a plus b by 2, and then y is basically a minus a plus b by 2. So 2a minus a minus b by 2. Correct? So if we take my x as this and y as this, and if we calculate the image of this, then we'll get a comma b. So indeed a comma b has a pre-image because this is in R2. Correct?
Yes.
So this is onto. So the answer is yes, this x comma y exists because we find x and y like that. And so the answer of this question is also yes.
Can you state the question for the second one once again,
Can
please?
you go, onto once again?
So for onto means what? So I have this mapping, right? R2 to R2. Let me write this mapping here. X, y. It is x plus y, x minus y. Okay. So if for checking onto, what we have to check? Take any element from R2, whether there is a pre-image or not. That means take any element a comma b from R2. Does there exist x comma y inside R2 such that t of xy equal to a comma b? Right?
Sir, A and B you are taking from the codomain, right?
Codomain.
Yes,
R2. Yes. Right? Yeah. So my question is whether there exists x comma y such that t of x comma y is a comma b or not. Now what is t of x comma y? T of x comma y is x plus y comma x minus y. Now, can we have a solution such that x plus y is a and x minus y is b? If we have a solution for x, y by these two equations, then we get the pre-image, right? Then we get the pre-image. Yes, we can find a solution. If we take x as a plus b by 2 and y as a minus b by 2, then t of x comma y is indeed a comma b. That is what we get. So a comma b has a pre-image. And what is the pre-image? Pre-image is a plus b by 2 comma a minus b by 2. Right? So there exists x comma y inside R2 such that t of xy equal to a comma b. So the map is on. Clear?
Yeah. Yes, thank you.
Okay. Now the point is, in this week, the lecture end with thus giving the definition of one and onto. For linear transformation, you don't have to check this much. There are much easier way in week 6. By seeing that, I mean the easier way, there are easier way to check the process for checking one and onto. So we'll discuss it in week 6 live sessions. So, but remember, don't be frightened that every time you don't have to check all this what I have checked now. Okay, there are some easier method to check one and onto for linear transformation, because this has some more property, right? This is what I am doing for mapping, exactly for mapping. But linear transformation is not only a mapping; it has some more property, right? It respect addition, it respect scalar multiplication, right? So we have to use that. So once we use that, it will give us some more property. By using that, we can directly calculate, directly check whether a mapping, a linear transformation is 1-to-1 or 1-to-1 or not.
So can you scroll down?
Sir, what I want to say is, in the activity questions, the mapping is from R2 to R3 and R3 to R2, and we have to check whether they are on-to or 1-to-1. Sir, can you take one example of that, which is 1-1 and on-to, and one example in which it is 1-1 and not on-to, and vice versa, sir? That would help to understand this concept better, sir.
R2 to R3, suppose I am taking Txy as x00. Is it onto? Is it 1-to-1?
No.
Why?
Because we can have 2,1 and it will be 2,0. You can have 2,2 and it still be 2,0.
Exactly. So in place of y, there can be any element. Eventually, it will give me the same image, right?
Yes.
So
sir, I didn't understand the reasoning, sir.
I am showing that. So if I take 1,3, what is the image?
1,0.
1,0,0.
1,0,0. If I am taking 1,4, what is the image?
Again 1,0,0.
0,0.
So two elements are giving same image, right?
Because I kind of y is useless.
Y is useless. So T is not 1-to-1.
Not 1.
Is it clear to everyone?
Yes.
Is it clear?
Yes, sir.
Yes, sir.
Everyone?
Yes,
everyone,
sir.
it is clear? Should
Yes,
I go ahead?
yes, sir.
Okay.
Yes,
yeah.
it is clear.
Now, is it onto? Is it onto? I mean, it is easy to say it is onto or not.
Yes, sir, it is onto.
Yeah.
It is onto? Can you give me a pre-image of 1, 2, 3?
No, sir. It's not onto.
It cannot be onto because the image will always be on x-axis, right? X, 0, 0. I mean, if we put anything in y coordinate and z coordinate, that cannot come as an image, right? So 1, 2, 3 does not have a pre-image, correct?
Yes, sir.
Clear? So it is not onto. So it is
when
not
we're
1-to-1.
Sorry, just one clarification here. When we say a pre-image exists, even if the transformation says x, 0, 0, I'm talking about t xy is equal to x, 0, 0. It should, when we say onto, it should be for any xyz, is it?
Because codomain is your R3. That depends on the codomain.
Okay, so if a codomain is defined as
only like x-axis on R3, then it is onto.
Then it is on. Okay, thank you. Thank you.
Yeah. So for this structure, it is not on-to-1, 1-to-1, not onto. Correct? Is it clear to everyone?
Yes, it is.
Yes, sir.
Yes.
Okay, great. Okay. Let me go a little bit further with this example itself. Another example, then it will be more clear. T R2 to R3 again. Txy is xy0. Now is it 1-to-1?
Yes.
Yes. Why?
Because when we take 1, 1, that will give 1, 1, 0.
Yes.
When we take
that is one example, but how we will prove that? So proof will be similar line, right?
X equals to X and Y equals to Y.
Yes.
The same thing we have to show.
Yeah.
Which is 0?
Not on.
Z is always 0.
Then, so?
Sir, we will not care about Z, right?
Let's go by definition first, because we only know the definition till now. Okay. So if there are two vectors in R2, which is going to the same element, same image, let's see what happened. Can there exist two such defined vector? So if I see that, then obviously x1 is x2 and y1 is y2. So there cannot exist two defined vector, right?
Yes, sir.
Yes.
So this is giving me, it is 1 to 1, correct? It is clear to everyone?
Yes, sir.
Yes, sir.
Yeah. Okay. Now my question is it on to?
No, sir.
No, sir.
Why?
Because our codomain
0 does not make any pre-image, sir.
And
can you give me one element which does not have a pre-image?
0.
1, 2, 3.
1, 2, 3.
Same thing, 1, 2, 3. Take anything in Z which is non-zero, that will not have a pre-image. Correct? Clear? It does not have a pre-image.
So this is 1 to 1, right? Or
so it is 1 to 1, but not on. Okay? 1 to 1, but not on 2. Clear?
Suppose in this transformation definition, you have written t x comma y equal to x comma y comma 0. Suppose 0 is not there. Suppose z is there.
But how the input z will come? There is no z.
Okay, sir.
Right? If it has to come there like R2 to R3, then it should be a combination of x and y. I can define it like this.
Sir, then
R3,
if there is anything else
R3,
0,
R3,
then
R3,
it not
R3.
1 to 1, sir. If there is anything else 0, then it is not 1 to 1.
Anything?
Else 0.
Anything else 0? You tell me, is it 1 to 1?
No, sir.
It is 1
It's
to 1.
not 1 to 1.
Yes.
I am getting two type of answer. So let me check. You check it, no? You know how to check, right?
Okay.
So you get first equation is giving x1 equal to x2, y1 equal to y2, and x1 plus y1 equal to x2 plus y2, right?
Yes.
So if these two are satisfying, then this one will also satisfy, and this is consistent basically. So indeed x1 equal to x2 and y1 equal to y2, correct?
Yes.
So is it 1 to 1 or not?
Yes, sir.
Yes.
It is 1 to 1. So it is, yes, it is 1 to 1. Now is it on to?
Yes. Yes.
No.
Are you sure?
No, sir. No, sir.
Can you give me an example which does a vector in R3 which does not have a pre-image?
1, 2, 3 again.
No, 1 to 3 have a pre-image. 1 to 3 have a pre-image, no?
1 to 4.
Yeah.
1 and 2.
4, 1 to 5.
1 to 5.
So basically the third coordinate cannot be sum of
Linked,
first two.
Some of the other
1, 1, 1.
So if you take here
1,
4,
1, 1.
then it does not have a pre-image.
Yeah.
1, 1, 1, that also.
there are many.
So there are many, infinitely many, does not.
Sir, suppose we have to check it algebraically, sir.
This is what I am doing. This is the checking by algebraically. No?
But 1 to 4 means x is 1, y is 2, then x plus y has to be 3, no?
Yes, that's why 1 to 4 is
For
not
image,
having.
that's why it does not have a
Oh,
pre-image.
yeah. Okay, got
This
it.
is inside R3, but it does not have a pre-image.
Got it.
Right?
Yeah, thanks.
Yeah.
So do we always have to do like this while checking on to?
No, we don't have basically. For this week, you just go with the definition because it's good to have definition in mind. But next week,
Okay, sir.
in the week's beginning of
Sir, I
week,
have
we'll
some
see
confusion.
different.
I have some confusion in applying the onto definition to it. Sir, can you explain me a little bit?
Yes, I have.
You tell me what is onto. You have learned in maths 1, right?
Yes, sir. I'm clear about sir on, but how do I check it? Like you have checked for 1-to-1. How do I check it for?
Example was onto.
Last example is not onto.
Okay.
Does not have a pre-image. No, 1 to 4
Yeah,
does not have a pre-image.
Yeah, it is not 1-to-1.
It is 1-to-1, but not onto.
Okay, okay.
1-to-1 I have checked, no? Here.
Sir, taking the same by going definition wise, sir, how can we check that?
Take one element from the codomain. Okay. For checking onto means what? Every element of the codomain has a pre-image, right?
Yes.
So if you take any element, suppose T is R2 to R3, you have to take any element from here, okay, and check whether there exists some element here or not, such that T of xy is ABC. If that happen, then it is onto. If that does not happen, if you can find one element in R3 which is not in the image of this T, then it is not onto. Is it clear?
Yes, sir.
Yes, sir.
By extension, can we say
is
that?
It clear?
Yes, sir.
Sir, does that mean in general that R2 to R3 mapping is mostly not onto?
Yeah, that is basically the case. It can never be onto. Okay, but there is a proper reason behind it why it can never be onto.
Sir, in tutorial 5, it has mentioned why this is tutorial 5. Sir,
yeah, but tomorrow we will explain it again. That's why I am not explaining it.
Okay.
Yeah. Because tomorrow I will define what is kernel, what is image, dimension of image and dimension of kernel. Then we can do it little bit easily. Okay. That's why I am not mentioning. So for now, just remember this definition. Then tomorrow we will start from here and we'll go. I mean, how we can check easily and what are the conditions when it can a linear transformation be onto, can a linear transformation be 1-1. There are some relation with dimension of the vector space.
Yeah, that's rank and nullity.
Yeah, that will come again. That's why I told you at the beginning that when we start week 6, you promised me that you will not ask again what is rank and nullity.
Okay, sir.
Okay. But okay, so you will see all this what we have discussed today. Then if you have doubt again, then we will again discuss tomorrow. Don't worry, because this need discussion. This need proper discussion. Otherwise, it will not get clear. So if you have doubt, we will discuss this again. Okay, don't worry.
Can I ask a question on the same definitions that we said for onto and 1-to-1? When we say can two pre-images have same image, that is how we are actually asking that question. We are determining that it is 1-to-1. If the answer is no, two pre-images cannot have same image, does it mean that some of the images can be left out?
That does not mean always, no?
Yeah, it can, however, in some cases mean. Is that?
I mean, there can be linear transformation which is both 1-1 and onto, right?
Yeah, that's also there.
I mean, yeah.
But
that is basically bijective.
So, but two pre-images cannot have the same image, right? Then it is
for
not
1-to-1 it cannot have. For 1-to-1 it cannot have. If it is not 1-to-1, then it can have, no? Like this one. This one.
1-to-1 must
two element can have same image. Then it is not 1-to-1, right?
Yeah.
It should be unique.
I mean, all the combinations are possible. It can be 1-to-1, not onto, can be 1-to-1, not onto, can be onto, not 1-to-1, can be both. Neither can happen. All these are possible. Okay. Okay, all the combinations are possible. I mean, 4 type of combination is possible basically. Both 1-to-1 and onto, 1-to-1 but not onto but not 1-to-1, neither 1-to-1 nor onto. Okay, all these 4 combinations are possible. And even I have given the example of all such, right?
Sir, may I ask one doubt?
Yeah.
Sir, it is in activity 5.5, sir.
Activity will you solve yourself?
Sir, actually, it is regarding some concept, sir. It's question number 8. It has not been discussed today, sir.
What is that? So in chat, I am just posting this form for getting who are attending. So at the meantime, you can.
Sir, I joined late.
So I will ask you to.
No.
I mean, I am sending this some private.
If everybody.
One minute.
Yeah.
Yeah. So can you fill this form? Yeah.
Actually, I joined late. 7:45 I joined. If possible, if everybody's question is over, little bit, can you touch on linear transform?
Can you go back and see the recording once?
Yeah. Okay. That anyway, better, I will do it. But at least 5 minutes.
Yeah. So
sir, let us,
do that.
Sir, at least discuss that concept, sir. That has not been discussed today. Activity question 5.5, question number 8, sir.
I am opening it. Let me see. Yeah, I will discuss the linear transformation once. Okay.
Okay. Thank you.
Okay. Week 5, no?
Yes, 5.5.
5.5. No?
Sir, are we done with the discussions?
So I will not discuss any more new concept today.
Okay. Thank you, sir.
If you can just fill up the form, okay?
So question number 8.
Question number 8. This one, right?
Yes, sir. So how do we get this equation, sir? From, because we are given transformation from this to this.
So can this 2,1 and 1,3 are these two elements? I mean, if we form a set with these two vector, is that set linearly independent? I mean,
yes,
is this
sir.
form a basis of R2?
Yes, sir.
Right? It form a basis, right?
Yeah.
Okay, good. Now, so any element of R2 can be written as linear combination of these two?
Yes.
Yes, sir.
Means
2, 1 and.
So what is given? Can you tell me? 2,1 is?
T2, 1 is 3, 2. And T1, 3 is 0, 0.
Okay. So this is T from R2 to R2, right? So any element of R2 can be written as linear combination of these two, that we know, correct? So any element, say A, B of R2 can be written as linear combination of, say, C1, 2, 1 and C2, 1, 3, correct? Can you solve C1 and C2 by this in terms of AB?
Yes.
What is the solution? 2C1 plus C2 is A, C1 plus 3C2 is B, right? Then what is the solution?
So we have to solve by...
solve it, no? This is easy, not so difficult, no? So 6C1 plus 3C2 is 3A. I'm just using your high school method to solve it. Right, so this is 5C1 equal to 3A minus B, right? So C1 equal to 3A minus B by 5, correct? And what is C2? A minus 2C1, 2, 3A
B minus A by 2.
B minus A by 2, is it? 5A minus 6A plus, not B minus A by 2, 2 coming, no? So 2B minus A by 2 by 5. Okay, so C1 and C2 I have calculated. So basically any element A comma B, I can write it as 3A minus B by 5, 2 comma 1, 2B minus A by 5, 1 comma 3, 1 comma 3. Right, till this part it is clear. I am just writing any element.
Yes, sir.
Using these two elements because this is forming a basis, right? That's why I can do it. So what is T of AB? If I use the property of linear transformation, then T of this means I can write this out, t of 2, 1, and then this also can be separated out by using both the conditions of linear transformation, right? I can write this because these are constant. These are real number, correct?
Yes.
Is this part clear?
Yes, sir.
Yes, sir.
Okay. Now what is t of 2, 1? T of 2, 1 is given, no? 3, 2. Are you with me or are you
Yes, sir.
lost?
Yes, sir.
Okay. And t of 1, 3 is 0, 0, right? So what is this? This is 9a minus 3b by 5, 6a minus 2b by 5, correct? So you know what is ta, b. This is your definition. This is what you get as your linear transformation, right?
Right.
So I think this is coming, right? 3. Okay. I mean, I have done with a comma b. You can there it is given by x comma y, nothing else. Okay.
Okay.
I mean, is
yes,
it clear?
Yes, sir. Yes, sir.
Okay. So basically, I have to use the property of basis and property of linear transformation. That's it. Okay. Yeah. So let me just recall once what is linear transformation. Then I will end the session. Okay. So linear transformation is basically, you know what a mapping is, right? Mapping is from one set to another, correct?
Yes.
You know, you have learned this in mapping in your Maths 1 course.
Yes, yes.
Now for linear transformation, instead of set, we are dealing with vector spaces. So linear transformation is basically a mapping from one vector space to another vector space. Now vector space have two more operations, right? One is addition and another is scalar multiplication, correct?
Yes, yes.
So this mapping, we want this map to respect those operations. What does that mean? So in V, I have V1. Suppose I have V1 and V2. Okay. Then this mapping takes V1 to TV1 and V2 to TV2. Correct? There is another element in V which is sum of these two, because sum of these two will also be inside V. That is V1 plus V2. Then this V1 plus V2 will go to T of V1 plus V2. Right? Now there has to be some relation between these three elements, because in this side V1 and V2, if we add these two, we'll get the third one. So here also we want some relation between these three vectors in W. So what is the relation we need to respect the addition? Basically, if we add this TV1 and TV2, we should get TV1 and V2. That is the ideal situation we want. That's why the first condition arises. Similarly, for the second condition, V goes to TV1, then there is, if you scalar multiple this one, so take CV, that will go to TCV. Then basically there should be some relation between TV and TCV, and how this we want this to be related. If we multiply C with TV, then we should get what TCV is. So this is how the second element is coming. So if in a mapping from one vector space to another vector space satisfy these two conditions, then we call it a linear transformation. Okay. Now, if you see that where does 0 go? 0 must go to 0.
Yes.
Because if these two conditions are satisfied, then you can check that 0 must go to 0. I leave the proof to you. Sarah has already proved this in lecture. So 0 must go to 0. So once you are given some linear transformation, some mapping to be checked whether it is a linear transformation or not, first you check whether 0 is going to 0 or not. So suppose I am giving this example. T of xy is going to 2x plus 5y, comma x minus y. Right? Now if 0, check whether 0, 0 is going to 0, comma 0. Yes, indeed it is going. Then you come to checking these two conditions. If 0 does not going to 0, then you need not have to check other two conditions, because then it is not a linear transformation. For a linear transformation, 0 must go to 0. Okay. So, and another thing you must remember, suppose I have a linear any mapping from Rn to Rn, then linear transformation means in this side there must be a combination of all these xi's, and that combination has to be linear. I mean, there cannot be any power. I mean, this x square cannot appear or x cube cannot appear.
Yeah.
Any coordinate cannot be take any power, cannot take any power basically. So it must be a linear combination. So any general linear transformation from Rn to Rm will look like this. Take any element from x1 to xn, any vector in Rn, and in this side there should be m linear combination of all these vectors, all these coordinates, all these xi's. Okay, all the linear transformations should look like this. So basically you don't have to bother to check all the condition. If you see a map like this, that will be a linear combination. If you see any power on any coordinate, then it cannot be a linear transformation.
Here also for t x, y, z, so it's 0 is there. 0 is 0, 0.
0 is going to 0, and it is a linear combination basically, as you can see, of x, y, z.
So for
it is a linear
space,
transformation.
for vector space, we are checking two means addition and multiplication.
Scalar multiplication.
Scalar multiplication.
Yeah.
Similarly, we are checking for linear transformation. 0 should go to 0 only.
That is the first check you do in your mind. Okay. That is not condition written anywhere, but it's better to check to begin with, because once you check this one, if this one is not satisfying, then there is no point of checking the other two. That's my point.
Okay, if there is a constant here, for example, x minus y is there, but if we have a constant 1 or 2, then
it cannot be a linear transformation.
Linear transformation. So that is first check. So can you go back to the first page, sir? Just only 5 minutes more. See here, t into v plus v2 you are telling, no? So we are mapping to the v is nothing but domain and w is nothing but codomain.
Codomain, right.
Okay, v plus v2. So means scalar means you are first checking the addition part, is it? Addition.
First condition.
First condition, and then CV is nothing but scalar multiplication. T means what? T is the
map. T is the map from V to W. V and W are two sets, right?
V and W are the sets, correct? That is the vector.
So T is the map between them. T is the map between them. So I mean, in set we use generally F or G, right?
Okay.
For linear transformation we use capital T.
So capital T doesn't have any other. It is just a symbol type. X comma.
Like this one, no mapping, map. It's a map.
Okay.
Like this. Here. This one.
So here you in this case where you have underlined x comma y is one vector, and that is the domain, and codomain is 2x plus 5y comma x minus y.
No, these are image. So this is your domain. This is your codomain.
Okay.
Domain and codomain are set, right?
Yeah.
And that's how the mapping is defined. Take any element of R2, that is x comma y, and it is going to 2x plus 5y comma x minus y. That is also an element in R2.
R2 to R2. Okay. And you have shown one example of R3 to R2.
I mean, now you can do anything. So I am giving you a general example for Rn to Rm. So Rn means any element of in coordinates, right? X1 to Xn. And in Rm, there must be a linear combination of all this.
Rn to Rm.
This type of
you are giving
a general thing.
General.
Now here, some coordinate to some coefficient can be 0. That doesn't matter. So yeah, basically all this form, this is basically the general form of linear transformation. General form. So all this linear transformation must be of this form.
Okay, here we have x, y, z, and here we have only two.
Two. So this is our linear combination of x, y, z, and here there is no y. So coefficient is 0 basically for y.
Okay.
Okay.
Sir, I need some guidance from you, sir. Sir, I have not been able to do the activity question 5.5 practice assignment. I have not done till now. And sir, I have to submit the graded assignment by tomorrow. So how should I approach, sir? Should I do the practice assignment first and then would be able to do the graded assignment?
So I am uploading the practice assignment right now after this session. You just go through it. Go through the practice assignment. Then I think you will be able to solve graded assignment.
Okay, sir. Thank you, sir.
Okay. Yeah.
Yes.
So here also same, no, sir? Like in max 1,
the definition is same.
On 2 and bijective.
The definition is same. Yeah. I think you have joined at this point, right?
Yes, I joined.
Correct.
Okay.
I will watch the YouTube.
Yeah.
Sir, the question, like 5.5 question you did earlier. From that, what I understood is that if supposing a TV1 supposing has been given to you, a value has been given for that, a W, and another TV2 and a W2 has been given, then in most likelihood, if you're supposed to find out for a particular V, whether you can find how we can find the W, then we usually test for the whether V1 and V2 are forming basis.
If the images of basis element are given, then you can completely found what the transformation is. That is the point.
So
of
whatever
this
we are given, whatever pre-images we are given and the images we are given, we must first check whether the pre-images actually form the basis.
So basically, you have to check whether you know the images of basis or not. If you know the images of basis element, then you can easily calculate the whole linear transformation, the description of linear transformation. Okay.
So in fact, the question itself is an indication.
Yeah, right. Okay. I hope you have, who are present in this session till now have submitted this form. Okay. So I am stopping the session now.
Can I ask one clarification? I know you already mentioned that you don't want to solve anything on activity questions, but there is one question on which I'm getting confused. If you can clarify that, if not solve it, it will be helpful. It is 5.511.
5.511. 1 and on 2 you have to check, no?
Yeah, I tried to solve it, but I'm not able to actually get past the first questions. Like I'm not able to resolve or get one. Basically, I'm getting 3 equations and 2 variables, both the cases. So I'm not able to actually, yeah.
So, there are 3 equations and 2 variables, right?
Yeah.
So if, okay. So suppose you take, you want to calculate which element are going to 0. Okay. Can you find more than one solution?
Which elements are going to 0? Can find. Yeah, if it is all equal to 0, then yes, I can have more than one solution.
Right. So there are many vectors in domain in R2 which are going to 0, right?
Yes.
So can it be 1 to 1?
It's got to be on to on that case, yeah.
It cannot be, right?
Yeah, it can. It has to be on to.
No, that doesn't mean it has to be on to. So at least it is not 1 to 1 that we know.
Correct. It is not 1 to 1. Yes.
Now for on to, what we have to do? You have to take any element from R3. Take A, B, C. Now can you produce a pre-image for that?
I'm not able
equation?
to.
Again, you have to solve the system of linear equation, no?
Correct. Here I'm getting 2x plus 3y is equal to A, 5x minus y is equal to B, and that is where I'm getting stuck. If I take it as A, B, C, if I take it as 0, then
have you solved it? Can you tell me the equations? What you are getting?
2x plus 3y is equal to A. 5x minus y is equal to B. X plus 6y is equal to C. So if I take it as A, B, C.
This is the augmented matrix, right?
Correct.
So what do you want to do here? So I am taking R3 and interchanging R3 and R1 to make it little bit easy.
Okay.
You can start with dividing the first row with 2 also.
Okay.
Nothing will stop you. So R3 minus 2 R1 and R2 minus 5 R1, right? Basically, can you solve this? This is nothing but solution, right?
Yeah, but I can have multiple values for at least 2 values for x and y.
But if you get multiple values for x and y, that doesn't matter. You need only one.
Okay.
Right?
Yeah.
For p-image of ABC, you need only one solution for x and y. If you have infinitely many, that's good. There are many pre-images. What does that matter? You have already proved this is not 1 to 1. So it's supposed to be like that. Right?
Okay.
Got it, no?
Yeah, okay. If I'm not able to solve, yeah.
So if you get multiple solution, I mean infinitely many solution, 1 minute. If you get infinitely many solution, what does it mean? There are many pre-images for A, B, C. It is not one-to-one, that is one thing. In the same thing, you can also say that this is also onto. Because for any ABC, you can have pre-images, right? There are many.
Sir, can I ask a question here related to this only? Sir, can you draw the mapping of a function which is one-to-one and onto?
One-to-one and?
Onto. The function is both one-to-one and onto. So
you want me to give an example?
No, sir.
Sir, before you
just
go
draw
to
the
that,
mapping,
can
sir.
I ask something related
Draw
to
the
this?
mapping means what?
Sir, like from domain to codomain, how the elements
so
would be
you want to give me an example, right?
Just mapping, sir. About don't take X, Y, Z and all that, sir. Just show the mapping, sir. How would the elements be related
X
in?
and Y, how can I show the mapping? I mean, I don't know what you are asking.
Actually, sir, while explaining the linear trans. Yes, a diagram, sir.
Diagram of what?
Of a function
like
which
mapping from domain to codomain with arrows,
which is one and onto both.
I mean,
yes, sir, like this.
Yes.
Suppose there are, but there is a problem. So remember, for set we can draw this kind of diagram, but here everything is infinite. Both the side has infinite cardinality. So I cannot take every element and get a pre-image here. This is onto for each element. Here infinitely many elements are there. And each element is going to one element, only one element. I mean, no two element is going to same one.
Okay, sir.
I mean, here I cannot put four dots and say this is one-to-one and onto, because it cannot happen, right? These are vector spaces. Once they are non-zero, there are infinitely many elements.
Okay.
Right? Can you tell me why there are infinitely many elements for a vector space?
Because, sir, we can suppose it is from R2 to R2. Whole of the domain is R2.
Suppose it has one dimension, then what does it tell?
It has infinitely many points in its domain.
Why?
Because it is a line, sir. A line has infinitely many points.
One dimension means what? Only one element will generate the whole thing, right? So span of this, right? So what is span of this? C of V. And C can take any real number. So there are infinitely many elements, even for one dimension. Okay? So for higher dimension also infinitely many elements will be there. Correct? So by drawing this diagram does not make any sense here.
Okay, sir. Got it.
Okay.
Sir, in this question you just did here, solving for it, you said if it has either infinitely many solutions or a unique solution, then we can say it is on.
No,
right?
Yeah,
That's what
right.
you.
Yeah, right.
So if
Right,
it has
right.
no solution, then it is definitely not. It's not on.
Then it is not
I
on.
want to ask. So over here, what I want to ask is, using this, can we also draw conclusions about one-to-one? That if it has infinitely many solutions, then it will definitely not be one-to-one.
Exactly.
So can we use this one? Can we do this just one thing to find out for both?
Yeah, exactly. You can do this. Okay.
Can I come back to my question on this follow-up?
Yeah.
Because I'm getting multiple values, the interpretation is that it is onto, correct?
It is onto and not one-to-one.
The problem is the answer goes the opposite. It says it is one-to-one and not onto.
So let me, this one.
Yeah.
So let me check. I don't know. Let me check it.
Yeah.
So 1, 6. So what? Tell me what is this solution?
5. Sorry.
So 0 minus 1 minus 31, right?
Yeah, minus 31.
B minus this is C, B minus 5C, and this is 0, 3 minus 6. This is also 0, right?
Yeah.
And this is A minus 2C, right?
Yeah.
So if A not equal to 2C, then A minus 2C is non-zero, right?
Yeah.
Sir,
then
the
0
last
equal to some non-zero number.
the
1
last
minute.
the
Can you
last row
just
is
hold on,
wrong,
madam?
I think.
Madam,
I think the last row is wrong. The last.
What should be there?
Okay, sorry.
I think it
minus
should
9.
be 3. Yeah.
Okay,
Minus
then minus 9.
Okay.
So what should be that? This is minus 9, right? This is correct, right?
Yes.
Minus 3 yes.
Then what should we do?
Amen.
Then what should we do?
So
Tell me. What
I
should we
have
do?
two possibilities for y.
Two possibilities for y. Yeah.
B minus 5c is equal
First, tell me, get to the row echelon form, no?
Yes, sir. Divided
Have you
minus
forgot
31.
it? I don't know. I mean, 1601 C
Yes,
B
sir.
minus
Minus
5
31.
C by minus 31, right?
Yeah.
0, and here also make
Take
it
0.
1. So R3 by minus 9, make it at the same time. So 1 and A minus 2C by minus 9, right?
Yes.
Then
we will remove. Then we can do R2 minus R3.
R3 minus.
R3 minus R2.
Yeah. R3 minus.
okay. So what does it mean?
No solution.
This is B minus 5C by 31 minus A minus 2C by 9, right? So 31 into 9, some huge numbers are coming. But my point is, this has no solution. Can you understand that?
Yes, yes.
Why?
Because it has 0.
0 no, but
0, 0 on the third row.
Basically 31 comma 9, and it has to be equal to 0, right? Now if this condition is not satisfied to be 0, I mean this what is this 9b minus 31a minus plus 17c. If this element is non-zero, then at the right hand side we have this element which is non-zero, but here it is 0, so it has no solution, correct?
Yes.
Who was asking that question?
I was asking the question, yeah.
So Ravi, it is giving no solution, not infinitely many solution.
Yeah. So, okay.
So, I mean, now tell me honestly, have you solved it?
I solved it. I made a mistake. I did not go for the reduced row echelon form. My intention is not to make you solve.
Always, that's why I am telling always, I mean, complete the whole procedure. Don't conclude from in between somewhere. You may go wrong for that. Okay.
Yeah.
So
yeah.
this is no
It's
solution.
not on
So
to,
that
sir.
means, so no, not on to. It is not on to.
It is not on. Okay.
Not on to. Okay.
Sir, how did you,
And it's 1 to 1.
sir, how did you conclude that there were a number of XYs which were giving 0? So that this was not
No,
one to one,
that's
right?
also not on to. I mean, that time he was saying that we are getting many solutions. That's why I said I have not checked.
No. Checking 1 to 1, but just looking at that the transformation,
If there are
you
more
were able to
elements which is going
conclude.
to 0,
How did you
there are more
conclude that? How did you conclude that?
If there are more than one element which is going to 0,
So it is 1 to 1, right?
then it is not 1 to 1. That's
No,
what
I
have
understood that, but how did you know that there were more than one?
No, I don't know. I don't know. I want you to check that. I don't know. I have not concluded anything. So you are saying this is going to be 1 to 1, right?
Yes.
No, what is your question? I mean, now she is not talking.
Sorry, I didn't understand. I'm sorry. When you were looking for 1 to 1, you said there were more than one XYs which were giving us the image 0, 0.
If there are more than one XY which is giving us 0, then it is not 1 to 1. I am not concluding that. I don't know what is the solution of this one. Okay. If you can find more than one XY for which you are getting 0 image, then it is not 1 to 1. That is clear, right?
Yeah.
Yes.
That is clear. That is the definition. If more than one, I mean, more than two element is going to the same element, then that is not one to one. But I don't know whether it is happening for here or not. Okay. So if you, for this case, you have to check whether it is one to one or not. So what was that?
So 2x1 plus 3y1. Can we actually write it as 2x1 plus 3y1 is equal to 2x2 plus 3y2, because that is what we are checking for.
Yeah.
No, sorry. Okay. 2x1 plus 3y2, comma 5x1 minus y1.
You tell me first of what is txy.
Yeah, txy is okay. Txy is equal to 2x plus 3y, comma 5x minus y, comma x plus 6y. Yeah.
So what you have to check? This one, right?
Yes. Yeah. x2 by 2. Yeah.
Yeah. So anyone have checked it?
I tried it. Basically, I put it as 2x1 plus 3y1 is equal to 2x2 minus 3y2. Sorry, plus 3y2. That's equal to 2 into x1 minus x2 is equal to 3 into y2 minus y1.
Okay.
The second one resolves to y1 minus y2 is equal to 5 into x1 minus x2. I mean the second one. That is 5x1. Yeah. Is equal to y1 minus y2. Sorry.
y2 minus y1. No?
Yes, yes.
No, y1 minus y2.
y1 minus y2. And the third one comes to x1 minus x2 is equal to 6 times y2 minus y1.
Now from here, can you calculate anything?
I cannot, because first one, that is on the right side, sorry, left side and the right side bottom, both of them are like, if I take the one on the bottom side, yeah, here, if I, the left bottom equation, if I take it as x1 minus x2 is equal to 3 by 2 into y2 minus y1, that conflicts with the other one on the right side.
How?
x1 minus x2 there is equal to 6 times y2 minus
write
y1.
It. So what does it give? Is it contradicting anything?
Yeah, it's saying basically 12 is equal to 3. If I subtract, I mean, sorry, if I cancel out y2 minus y1, it says 12.
Now, how you can cancel out? You don't know whether it is 0 or not.
Yeah, okay. Okay.
Right? You cannot divide with 0, right?
Yeah, okay. So 12y2 minus 12y1 is equal to 3y2 minus 3y1.
Okay.
Then basically it's 9y2 is equal to 9y1. So
you see y1 equal to y2?
Yep.
And if you put it in any of the equation, you will get x1 equal to x2?
Yeah, I made the mistake at y2 minus y1, I cancelled it. That was my mistake.
Yeah. Okay. So it is clear, right? This is on 1 to 1.
1 to 1. So we cannot cancel out because we don't know what it is going to be. That's something. Yeah. Okay.
I mean, how you can divide with 0? I mean, we don't know whether it is 0 or not.
Yeah.
Right?
As I said, yeah, that was the mistake. Yeah.
Yeah. So is it clear to everyone?
Thank you. That helps actually. I was struggling with that.
Yeah. Okay. I think Divya is saying something on this, right? Divya, are you there? No.
Yes.
Okay.
Yes, sir.
Yeah.
Thank
so
you.
now
I
it is clear,
understood
right? It is
just
1 to 1, right?
yes, very much so. Yeah, very much.
Okay.
Thank you.
Yeah. So okay. So let's meet tomorrow again with the next week 6 content. Okay.
So tomorrow it is at 8, correct? Right?
Tomorrow?
It's at 8 o'clock, right?
Tomorrow is at
8 o'clock or 6 o'clock?
8 o'clock, I think. No, tomorrow 8 o'clock. No? I forgot. Let me see. There is a calendar.
Tomorrow is at 6.
Tomorrow 6 at 6 o'clock.
Oh, again at 6.
Yeah.
Okay.
It will be covering week 6, right?
We'll start with week 6.
Tomorrow's section is week 6.
Okay.
Okay, sir.
Okay.
Thank you.
Yeah.
Thank you very much.
Yeah.
And
thank you, sir. Good night.
thank you. Thank you for your
Good
patience.
night. Good night.
More importantly. Good night.
Good night. Good night.